to control or to keep control of the people in this room. Otherwise, they have to watch, let's say, the workshop in YouTube.
Right, but you need to make, you need to do something to allow me to show my slides, or is that easy?
We need to allow you, right?
Yeah.
Oh, okay, I think it's now ready.
Okay.
Is it okay now?
Do you want me to try showing them or not?
Can you try it?
Okay, so I'll pull them up then. Do you see them or not? Do I have to hit something else?
You have to hit the green button.
Yeah, I know I have to hit I had to share screen, right?
Right.
And then
There we go.
There is it.
So does that look okay?
Yes, I mean at least here it looks verified.
You can see my pointer?
Yes.
Okay. Most important thing, piece of technology other than.
Okay, so let's just wait. I don't know, 3 more minutes just to allow people to get into the room. And as you know, we are not very famous here in Mexico for our punctuality. And let us give them 3 minutes. I mean, yeah, we are more or less on time, and we will have plenty of time still, unfortunately, because of the absence of Rosana. Hi, Magdaleno.
Hello, Magdaleno.
Hey, Magdaleno, how are you?
Ken, it's a great pleasure.
I see you there as well.
Good to see you, yeah.
Good to see you.
Hi, Ken. Hi, Magdalena.
Oh, hi, Grzegorz.
Hi, Grzegorz. Great to see you too.
We don't see you. I only see
We
you.
just see your name.
No,
Yeah.
now you should see me.
Now,
Yes,
now we
now
can
we
see
see
you.
you.
Hi, Grzegorz. Nice to meet you finally.
I see. Looks like he's in his living room also.
Yep.
Must be late for you, Grzegorz.
No, right now it's 2 p.m., so it's okay. No.
Oh yeah, that's right. Yeah, you're in this continent. Jesus.
I'm on this continent right now.
It
How are
is
you, Ken?
great for Thomas Hoydman, who told me that he will be here, like listening and so on. He will be on a train, but he asked me for the Zoom link and so on to be at least hearing to all of you.
Yeah,
So,
for him it will be late.
Exactly. And for
Ken,
Itamar
are you-
Prokasia even later, right? In Israel,
For
I suppose he is.
Itamar, yes, it's even later.
And I'm not sure if he's joining and so on. But we still have 2 minutes. Who else is in our room? It's complete. Okay. Okay. So then,
Ken, are you at home or are you teaching from?
Yeah, no, I'm at home. I've actually, largely, I'm still working at home. I have to go in to teach. That's about it. We have to wear a mask. We have to wear a mask everywhere in the buildings, and most of our faculty meetings are online, Zoom, and you know, my postdocs are happy working remotely, so it's not a lot of reason to go in. Once in a while, I'll go.
Yeah, it's the same situation here. There was a very brief period of time that we didn't need to wear masks, but then Delta came and.
Yeah. Fortunately, I was on vacation for a month in the Southwest during that brief period of time. I didn't wear a mask for a month. Then I came back to Champaign in the middle of July, and then things changed again. Right? So.
Yeah, we even went to Poland, and this was okay. I mean, didn't have to wear masks except for indoors. But this was at the very beginning of the summer before the whole thing sort of restarted again.
We'll see.
Yeah, it has been a hard time everywhere. Also here in Mexico, we were recently in a third wave of infections. Fortunately, now it levels and it's going down. But one has to remain careful. That's.
Yeah, one has to be careful. And unfortunately, in the US, this wave was quite substantial. So
Yeah, yeah.
Okay, so we are now in time. So is it okay if we start with our first session? I will just giving a small welcoming message and then we can start. Is it okay for all of you?
Mm-hmm. Yeah, sure.
Okay, so to everyone, good afternoon and welcome to the inauguration of a fall international workshop on matter out of equilibrium. As many of you already know, this time this workshop is meant to join the celebration of the 65th anniversary of the Institute of Physics of the Autonomous University of San Luis Potosí. Before introducing formally our distinguished guests and participants in our first roundtable, I would like to make a few relevant announcements. The first is that unfortunately, Professor Rosanne Sia had a family mishap and will not be able to attend our discussion. So on behalf of the organizing committee, and in view of the fact that this session is being recorded for later broadcast on our YouTube channel, I would like to take this opportunity to send her my best wishes and blessings so that soon we can count on her virtual presence and participation. Rosanne, my best wishes. Before officially starting the event, I also want to briefly thank to all the organizing committee for the tremendous effort and work, all that work invested made possible the realization of this series of discussions in a remarkably small time window. So also important, I need to thank to the University of San Luis Potosí, the National Council of Science and Technology, CONACYT, and the National Laboratory of Out of Equilibrium Matter Engineering for all the financial support that made this event possible as well. And last but not least, I want to deeply thank all the participants in our roundtables for their great willingness and openness to help us build this workshop. I'm convinced that the outcome of the event can be of enormous scientific relevance, allowing to build strong collaboration among us and the exchange of ideas, perspectives, and more crucially, the generation of new scientific knowledge. As all this already happened in the previous editions, and I'm convinced that it will be the case. So, although this is supposed to be very friendly and open discussion, there are some standard formalities to be attended here. So I must start by introducing our guest for today's roundtable, which is entitled Fundamental Open Issues of the Glass Transition. So the first panelist that I want to introduce is Professor Kenneth Schweitzer from the University of Illinois, Urbana-Champaign, which is a professor in material science, chemistry, and biomolecular engineering. And he will share a contribution, which is, let me see. Okay.
Can you see it?
Yes, I see it. I had another title, but well, now we have this phenomenology, fundamental questions, theoretical ideas. Okay, so I think it is time for Professor Schweitzer to share his screen and start our discussion with 35 minutes, and then we will have a small break of 5 minutes for small questions, and then at the end of the roundtable, we will have 30 minutes for discussion with all the participants, and we will try to keep these 5 minutes for the people in the roundtable to discuss. So, Professor Schweitzer, it is a great honor to meet you finally, and thank you very much for accepting the invitation.
Gracias, Cristina, and buenos tardes. So I want to first thank Pedro for the kind invitation to speak at this interesting mini symposium. And I'm maybe going to be a little bit of an outlier because we discussed with Pedro, I would give a discussion not on non-equilibrium, but on the equilibrium part of the problem. So I titled it Journey of an Equilibrium Liquid to a Glass, Dynamics over 14 or more decades in time. And the talk is not meant to be aimed at theorists even necessarily. I'm not going through detailed equations. I'll show a few. I want to discuss the phenomenology, some fundamental questions in my opinion, and go over a few theoretical approaches in the 35 minutes I have. I want to have some time at the end to give my own opinion about the broader relevance of the basic problem in many areas of soft matter physics, and especially in material science and biology. Okay, so let's see. Okay. So there's a wide world of glass-forming liquids. Rosanna was going to talk about colloidal suspensions, so I'm going to, she unfortunately won't be able to join us, so I'm just going to say a few words about them, but they're not my focus. The colloidal systems are amazing because they're designer systems via chemistry. You can manipulate the interactions to be essentially anything you want. And nowadays, the colloids can be hard, they can be soft, they can be spherical, they can be non-spherical, and you can tune the size over a wide range. And you can't do these things as easily with molecules. Now, there's a number of notable and unique features of colloidal suspensions because they're mixtures. There's solvent-induced hydrodynamic interactions. There's quench disorder associated with size polydispersity. The key parameter is usually not temperature, rather it's volume fraction and controlling the chemistry, hence the interactions. And the presence of strong short-range attractions leads to the unique ability to form long-lived physical bonds, which in concert with percolation can lead to a different form of effectively arrested matter that we call a gel. One practical thing is if a traditional colloid is a micron in size, this means that you can only access of the order of 4 or 5 orders of magnitude of slow dynamics in equilibrium before you fall out of equilibrium. Now, my interest in this talk is glass-forming liquids, and so one-component liquids, I'll call them thermal liquids, and in particular, 2 broad classes, molecules, a few of which are shown here, and polymers. And what they're characterized by is very diverse shapes. It's the world of chemistry. And they also have diverse interactions at some level. They can be polar, they can be nonpolar, they can be hydrogen bonding. And in polymers, we have the extra twist of conformational flexibility. Of course, there's also glass-forming hard materials, metallic mixtures, ceramics, ionic, which I will not be discussing in this talk. From an applications point of view, there's many diverse applications in material science. They're typically in the amorphous solid state below TG, in which case one has to deal with non-equilibrium phenomena, such as aging, which is topics that Greg and Pedro will discuss. So in the lab, forming a glass at TG is kinetic. That is, the system falls out of equilibrium. And we speak of structural relaxation and different probes of structural relaxation, some of which are listed here experimentally. And that's generally boiled down to some mean characteristic time scale, which I'll call the alpha time, which depends on temperature, density, pressure, and chemistry. So from the practical point of view, the glass transition is when you fall out of equilibrium, which is when this time scale exceeds the experimental time scale, which is of the order of 100 to 10,000 seconds in a typical experiment. And if you want to understand how the viscosity changes or the diffusion constant changes, yes, they're not the same properties, but to 0th order, the alpha time also controls their spectacular changes with things like temperature. So here's my key plot that really the talk revolves around. What I view as still the central problem is to understand this relaxation map of structural relaxation that can span 14 to 16 orders of magnitude in equilibrium. So what's plotted in a schematic way is the log of the alpha relaxation time versus inverse temperature, going from picoseconds to 100 to 10,000 seconds. People often have talked about that there's 3 regimes here. At high temperature, there's a straight behavior, which is an Arrhenius regime, although it's not really simple in the sense of being understood. At low temperature, you may have 8 to 12 orders of magnitude of strongly non-Arrhenius behavior. We call that the deeply supercooled regime. And you can think of it in the sense that the barrier is temperature dependent and growing. Below TG, you fall out of equilibrium, and what happens in equilibrium as you go further up is not well understood. In between, there's a crossover regime that different people think different ways about. One idea about it is that there could be a critical power law in here. I'll discuss this at some detail shortly. Now, if you believe in these 3 regimes, then you have 2 crossover temperatures and 2 crossover times, and it's interesting to know about them. So fragile liquids have this pattern of relaxation, molecules, polymers, metallic mixtures, but there's gigantic quantitative variations on top of the general behavior, which are very interesting, at least to me. The purple box is basically where the world of simulations and colloids live for different reasons. They're effectively trapped in a crossover regime where you can probe nowadays maybe 6 orders of magnitude, but that's far less than what you can do for thermal liquids in a laboratory. I think it's fair to say that understanding this from a fundamental physics point of view remains a grand challenge, and it's conceptually contentious in the sense there's lots of different models and there's no consensus on how to understand such a plot. So I want to discuss a few zeroth order questions, and these represent my own opinion, which I was asked to give. And most of these questions revolve around the physical mechanism of slowing down. So the plot on the right is just a characteristic result for a molecular liquid over 16 orders of magnitude. So here's the questions that I will pose. Are there really 3 regimes? I mean, is there different physics in these regimes? And if there is, what's the origin of the crossovers? What causally controls this explosive growth in the non-Arrhenius regime? Is it thermodynamics? Is it structure? Or is it neither, or something else? What happens in the so-called deep glass state beyond TG if you could stay in equilibrium? Or in the language of the potential energy landscape, if you went below TG and you still have metastable states, what would happen to the time scale? Does it diverge at finite temperature or not? Is there an equilibrium phase transition to an odd amorphous solid? When you get more detailed, you need to ask questions about what you think is the specific order parameter, quote unquote. And here, the number of different postulates is tremendous. In the thermodynamic category, it's been proposed it could be entropy, or enthalpy, or compressibility, or internal energy, or free volume. At the level of the structure, the simplest level of structure is the pair correlation function. What I show here is a G of R of hard spheres, where you see the local correlations, which are enhanced upon increasing density. But maybe what's important is some higher order correlation function. Well, maybe it's not these. Maybe you have to go straight to dynamics, but some type of simpler dynamics. Maybe the elementary thing is something about the shear elastic modulus, or some short time localization length, or various mobile defects that have been discussed in the literature. Another question is the role of or existence of a static or dynamic length scale. And does that length scale grow? Is it really the key to understanding this growth of the relaxation time so spectacularly? One of my favorites, as you'll see, is the real space nature of the rearrangement event. Is it something compact? That is, the rearrangement event occurs in some localized region of space? Or does it involve very long-range physics? Or is it something in between, as Jeppe Durr has discussed, where there's a coupling of local rearrangement and long-range elasticity? And finally, I remain fascinated by these endless empirical connections between dynamics on long times, the alpha time, seconds, and dynamics on very short times, picoseconds and nanoseconds. How do we understand that? Well, there's many, many different theoretical approaches. And the reason for this is it's a very difficult problem in statistical mechanics because it involves activated dynamics and rare events. The presumed key physics in the different approaches are often totally different. And one might think that, in fact, in many cases, they're mutually orthogonal. Part of the problem is many approaches are not truly predictive. And by that, I mean that when they confront reality or computer simulation, there's fit parameters, and the ability to deal with the incredibly rich non-universal chemistry effects is highly limited. So what I'm going to do today is I'm going to sketch 3 very different approaches, one from sort of 3 different categories that I'm most familiar with myself. The first is a thermodynamics scenario, the configurational entropy crisis. The second is non-activated, locally correlated dynamics, where it's all about the so-called cage effect. And the third is a more solid-state physics perspective, where the focus is on activated hopping and collective elasticity. So first, configurational entropy. Let's remember what it is. we have our cartoon of the potential energy landscape that consists of many locally stable amorphous packings. And the configurational entropy is essentially counting the number of these local minima. It's local minima, so it's a thermodynamics concept. And that as you go down in temperature, that you lose these minima. And so configurational entropy decreases as you cool. So determining the configurational entropy has never been very easy. One can approximately extract it experimentally, and there's been recent novel simulation approaches that have been able to get a handle on it with simulation models. So there's this very nice summary of configurational entropy by Ludovic Berthier and co-workers in a JCP recent perspective that shows the configurational entropy in a normalized way as a function of cooling. Of course, the configurational entropy goes down as you cool, but the way it goes down is very non-universal. You needn't worry yourself about these precise systems. Some are experimental, some are computer simulations, some are in 2 dimensions, some are in 3 dimensions. So it's very non-universal. And then the question is, what happens as you go farther down? A popular idea is to extrapolate. If you do, you then conclude that there is a vanishing of the configurational entropy at a finite temperature, historically called the Kautzmann temperature. And well, is that real is one question. And second, is it impelling a phase transition? So this is the configurational entropy. Now, what do you do with the configurational entropy in thermodynamic theories? And there's many workers who have worked on this. It's an incomplete list. There's many versions of this. I'm going to talk about the older version because in the end, at least what little I want to say about this, it seems like it doesn't matter much. The basic assumption is that thermodynamics controls dynamics. And the assumption is it's configurational entropy that controls the dynamics. Now, configurational entropy is a property of the minima of the landscape, right? It's an equilibrium thermodynamic property. So assuming that that controls the barriers, which are dynamic, controlling dynamics, at least literally, their maximum on the potential energy is an assumption. And figuring out why this might be true remains a grand challenge. Now, if we go back to Adams and Gibbs, there was a simple real space picture that there's some compact region of a finite number of particles. Those regions are independent in the liquid, and rearrangement in that region, called a configurationally rearranging region, is what the event is that we call the alpha process. And then you can think about either their size is growing as you cool, or the number of units that are moving cooperatively grows as they cool. And the reason is argued to be because you're losing configurational entropy. So at 0th order, the modern and the classic ideas claim then that the dynamic barrier scales inversely with the configurational entropy, meaning you can write the alpha time this way, where the configurational entropy is either in the denominator with some unknown constant that sets the right units. It might be a bare activation energy, or you could write it this way, the way Adams and Gibbs did, where there is a bare Arrhenius activation energy and the number of rearranging units grows with temperature. But this quantity grows inversely with configurational entropy. So that's the idea. If the configurational entropy in fact did go to 0, then you would have a divergence of the alpha relaxation time. So again, I'm not an expert in this area, but I read this interesting second perspective of Berthier et al. That tried to evaluate the configurational entropy idea. And so here's one snippet from this paper. So here's a bunch of experimental data over 13 orders of magnitude, alpha time versus inverse temperature. So if this formula was correct, then if you plotted the log of this versus 1/T times configurational entropy, the data should be straight. Well, at least for these of the order of 10 systems, the data is not really straight. In fact, you can look at the data on time scales that you can probe on the computer. This would be where the TG on simulation is and where TG is experiment is. And it's occasionally it's straight on one of these. It seems to be never straight on all of them, but overall there's a lot of curvature. So it's not straight, at least it's not straight in my eye. And this led to the idea, and there's some theoretical arguments about this, that, well, maybe it's not 1/configurational entropy. Maybe you have to raise it to an exponent. So you can do the empirical exercise of varying the exponent on a system by system basis to try to straighten this. But remember, floating the exponent is changing the entire temperature dependence of this function. So you can more or less straighten this data by changing the exponent, and then you can ask, what do you need to do? So here's the plot from the paper. What the exponent is, Adams-Gibbs and the elementary RFOT would be 1, but the alpha is massively variable. It depends on whether you are analyzing in the simulation window, that's the black points. It depends on whether you're analyzing in the experimental window, that's the red points. It depends on the system. The exponent can be much larger than 1 or much less than 1. So to this is very worrisome to me, and what you want to conclude out of this is up to you, but speaking for myself, I find this troublesome with regards to the configurational entropy scenario. So the other two approaches I want to sketch is particle level approaches, where you try to work at the level of particles and forces. I'll call them microscopic dynamical approaches. And their general philosophy is that of liquid state physics, where dynamics is not causally related to thermodynamics as it is in, for example, the entropy crisis theory. So here you start with a system that has a given interaction potential, a given thermodynamic state, and then what is the chemistry? What is the system? And the first thing you ask is, what is the equilibrium packing structure? And the simplest version of this is the pair correlation function, G of R, which is here I've shown as I did before for hard spheres. And then the basic idea is, because you have this correlated structure, especially on local scales, that a particle trying to move will tend to be blocked. Of course, all the particles are blocked by trying to move, and this is called the cage effect. And the thought is that this could be the origin of the large slowing down at some level. It may not be the whole story. But you use this knowledge of correlated structure to construct dynamical constraints via effective forces. And so from that construction of effective forces related to structure, you attempt to predict the slow dynamics. And so that's the overall zeroth order philosophy of a number of different approaches. Then you have two choices to try to understand the problem at the level of the ensemble average, which is how experimentalists do it, unless they're observing trajectories in a confocal microscope. And the prototypical example for that is ideal mode coupling theory. There's also very nice work done in this direction at Saint Louis Potosi. And then there's a second approach, which is my own work, is to not work at the ensemble average level, but try to work at the stochastic trajectory level, which I will argue is, of course, it's approximate, but it's a beyond the mode coupling theory approach because it focuses entirely, essentially, on activated dynamics. So let me discuss the first approach very briefly, which is a seminal approach, the ideal mode coupling theory. So the core idea is that the key slow dynamical variable is the collective density fluctuations. They are directly measurable in this dynamic structure factor, S of K and T, which is the autocorrelation function of the density fluctuation of wave vector K at time equals 0 with the density fluctuation at wave vector K at a later time. And this is measurable in many experiments. Now, there's multiple approximations in the mode coupling theory, as there are in all theories, but the strongest one, in my opinion, is a Gaussian or diffusive-like description of collective motion. The consequences of this is that you get a closed equation for the dynamic structure factor, but you've given up the ability to a priori predict non-Gaussian processes like the activated hopping. Having said that, the beauty of the approach is that you can relate dynamic forces and their constraints to the pair structure. So if you know the pair structure in real space, or technically generally in Fourier space, here's the structure factor. So as you cool the liquid, you have more and more correlation locally, that you can predict dynamics. And in mode coupling theory, although there's more advanced versions of it, but generally one views that the most important part of the structure is the local structure. Now, in this approach, long wavelength fluctuations, which are in the structure factor and are related to thermodynamics, are not playing an important role, at least as far as I understand. So then you can self-consistently solve for the dynamic structure factor, and this work has now been around for over 3 decades and has been tremendously valuable. Rich dynamical behavior is predicted by the mode coupling theory as a function of time and length scales, and here's 2 prototypical results. The first is the dynamic structure factor normalized at time equals 0 on the scale of the cage versus the log of time. So this is a schematic, but if the temperature is high enough or the density is low enough, then you get a simple relaxation process that's roughly exponential. As you increase the packing fraction or lower the temperature, you get a bifurcation. You get two processes and you begin to get a plateau. And this is associated with some long-lived caging process. And as you increase the density more or you lower the temperature more, this plateau becomes more well-defined and the time scale becomes extremely long. So this is a giant success of the mode coupling theory. In my language, I would say it's really been wonderful for predicting the onset of this transient localization and this bifurcation of the relaxation spectrum, the two-step relaxation. It also predicts many other things I don't have time to talk about. The problem as I see it, and I think nobody probably disagrees, is that the time scale it predicts for relaxation obeys a critical power law. And so it actually predicts there's a divergence, which is typically far above the glass transition in the lab or above the volume fraction in experiment. And it predicts that the relaxation time, the viscosity, the inverse diffusion constant, they all follow such a critical power law with an exponent that is predicted from knowledge of the structure. So here's some work from the Montpellier group, both experiment and simulation, which shows over about 6 orders of magnitude, which is pretty much the state of the art, the log of the alpha relaxation time versus volume fraction. The points are the simulation and experiment, and the curve is the mode coupling prediction of a critical power law. And you see that it can be fit. The exponent is predicted. It just needs to be moved around where this divergence is. It can be fit to the data over about 3 to 4, maybe 4 orders of magnitude. And then it appears to disagree because the theory predicts a strict divergence without hopping and the experiments continue. So my belief, and I'm not sure anybody disagrees with this, is that the divergence is an artifact of the approximation and signals a crossover. And what's missing is the ability to predict rare, enormously non-Gaussian processes that at the single particle level we could call hopping. So the third theory is then a couple snippets of my own work over approaching 2 decades. To not throw away mode coupling theory, I think it's a beautiful place to start, but to build on it to try to address hopping in a direct way and with a different starting point. And this is the nonlinear Langevin equation theory. And so the initial version of this says, don't work with ensemble average quantities, try to develop a stochastic equation of motion for single particles, which is what you get when you look at a computer simulation trajectory or a colloids in a confocal microscope. And so if you like, the order parameter is actually the dynamical variable, the displacement of a particle from its initial position. And then through both physical arguments and some level of coarse-grained dynamic density functional theory, we came up with this nonlinear Langevin equation theory, which is really a force balance between local friction, noise, and something else. And of course, all the physics is in the something else. It's an effective force that depends on the displacement of any given particle. And it's representing the cage effect. And that effective force using this idea can be constructed from knowledge of G of R or S of K, just as mode coupling theory. And so it's predictive in that sense. And so this quantity then we call the dynamic free energy. Its negative gradient is a force. And that's a new concept that's now been around for a long time. It's not new in that sense. The form of this beyond the mode coupling transition is this. It has this form that's sketched in blue as a function of displacement of a particle. So if a particle has a trajectory on this, it moves, it gets trapped at a distance we call the localization length. And then through random fluctuations, it ultimately surmounts the barrier with a jump distance that's predicted and a barrier that's predicted. And identification of the mean time scale for this using Promer's theory is identified with the alpha time. So this was a nonlinear Langevin equation until maybe 5 or 6 years ago, in which we took seriously an idea of Jeppe Deur that it's probably unlikely that this activated hop can happen without active participation of particles much farther away. In fact, if we take the theory seriously, the numbers that are predicted here, it's consistent with, in an average sense, not being able to realize this hop unless you have a small expansion of the cage. But you're in a dense system, so the only way to have a dynamic fluctuation that expands the cage a little bit is for the particles outside to move. And so the theory predicts that this radial cage expansion exists, and it's small, and we adopt the idea that it's required to allow a local hop. And so this then leads to the elastically collective NLE theory, or the ECNLE theory, in which the activated event involves some local hopping on a cage scale, but with the active participation or facilitation by a dynamic fluctuation of particles outside the cage. So the small cage expansion leads to a scale-free long-range displacement field given by this expression. It pulls off as a power law, that's what scale-free means, and the amplitude is predicted from the dynamic free energy. So then if we sum up all the displacements in the far field, there's an elastic energy cost that we associated with the barrier. And it can be numerically and analytically shown that this elastic barrier scales as 4 powers of the microscopic jump distance and 1 power of the dynamic elastic shear modules. So the physical picture then is of a coordinated mixed local non-local process, is what the alpha process is. And the barrier has a local part and a non-local part, but they're intimately coupled because everything that determines them comes from the dynamic free energy and hence G of R. When you then apply the theory predicts that the elastic barrier is a much more sensitive function of cooling or increasing density, and this is mainly due to the emergent rigidity that's happening in the far field. And this dominates the deeply supercooled regime. The other point to make about this approach is there's no divergences above 0 Kelvin or below random close packing. So I want to tell you about a couple recent results that have just been published in this PNAS article that we're particularly excited about. And the title is that there's a 6-fold degeneracy in how to think about the physical content of ECNLE theory. These have been deduced for hard spheres. So fundamentally, ECNLE theory is trying to predict barriers. The log of the relaxation time goes as these barriers. These are computed with the dynamical ideas I've sketched. But because it's a microscopic theory, we've been able to establish that the barrier scales with 5 other experimentally measurable quantities. The barrier scales as the inverse 3rd power of the dimensionless compressibility, which is a thermodynamic property. It's a theorem that it's the long wavelength value of the structure factor related to the integral of G of R minus 1 equal to the isothermal compressibility equal to the mean squared amplitude of density fluctuations. So the theory predicts there is a connection to thermodynamics, even though the theory is not formulated at all in terms of a thermodynamic scenario. The theory predicts that the barrier scales as 6 powers of the static correlation length of G of R in real space and 6 powers of the Fourier space order parameter, the peak of S of Q. And the theory predicts the barrier scales with 2 short-time dynamical properties, which are predicted by the theory, the localization length, which is the minimum of the dynamic free energy, and the dynamic shear modules. So this provides, I think, a unified perspective in the sense that it's just one theory, but all these things are consistent with the ideas of it. So this, I believe, reflects some of these reflect deep connections between thermodynamics and structure, such as the first one, and the other reflects the idea, which is really also the mode coupling idea, that slow dynamics on all time and length scales is related to structure. Now, all these predictions are causal. That is, they're directly related to the core ideas of the theory, with one exception, the connection to thermodynamics. The theory is not relating thermodynamics directly to dynamics. However, you can test it. Because the theory predicts the log of the relaxation time scales inversely with the dimensionless compressibility, you simply go to the literature, and it's in this recent paper. You look up the relaxation time of many systems. Here's 6 of them, 6 molecules. This is experimental data. and is plotted log versus 3 inverse powers of the dimensionless compressibility. So this is experimental data. This is an experimental data. And so this prediction would have support if the data lies on a line. And of course, it doesn't perfectly lie on a line, but it lies well on a line in the deeply supercooled regime, which is what this prediction is for, over something of the order of 8 to 13 orders of magnitude. So it works well, which is consistent with the theory, but it's not causal. We're not saying this proves that the glassy dynamics is controlled by thermodynamics. In fact, we're saying just the opposite. If we go to the low temperature, deep glass regime, then we can't trust this connection to thermodynamics there. We don't know much about the thermodynamics. We're using integral equation theory to determine the input to the theory. But we can use this connection that predicts the alpha time grows exponentially with a shear modulus over KT times a number. And so if you're at low temperatures near the bottom of the landscape, it's entirely reasonable to imagine that shear modulus is almost constant. And if it's true, then the theory would predict a low temperature crossover to an Arrhenius behavior. And I think Greg McKenna will discuss this phenomena from his perspective. Okay, now I want to only very briefly say something about older things in the literature. Of course, we can calculate the alpha time for hard spheres. This is 15 orders of magnitude versus volume fraction or compressibility factor. The full EC and LE theory is this. If we turn off collective elasticity by hand, we get this blue behavior. And so this is a log linear plot with the compressibility factor. And so it essentially says that NLE theory is about non-cooperative hopping. This is an Arrhenius-like behavior, while all the non-Arrhenius part is coming from the collective elasticity. We've compared this to hard sphere colloid experiments and simulations, which is a small snippet of this, and there's good agreement. Now, I don't have time to discuss it, but my real interest is thermal liquids and these 14 orders of magnitude. So we've developed mappings where we force the theory, we map a molecule to a hard sphere, but we force the properties of the hard sphere to exactly agree with the experimental dimensionless compressibility of thermal liquids at atmospheric pressure. And when we do that, we can make no adjustable parameter predictions for the alpha time of molecular liquids. And so here's an example. I don't want to discuss it in detail. For those of you who know some chemistry, here's 5 of the molecules. What's shown here is the alpha time. Again, there's about 14 orders of magnitude. It's an angel plot, TG over T. There's 4 experimental systems in here. They just happen to overlap because their fragilities are similar. And there's 4 theoretical curves in there that are not fits. So of course, there's not perfect agreement, but we think it's probably the level of agreement is far better than you should ever expect. So there's no fitting. And since part of me is a physical chemist, I was happy to see that the ideas do not work as well for hydrogen bonding systems. That is, mapping a hydrogen bonding system like glycerol to an effective hard sphere must be a more severe approximation. So we conclude that for nonpolar molecules, the theory is quite accurate over 14 decades. It allows us to have a physical understanding of the crossover times and temperatures. We're able to predict TGs almost quantitatively. And so ultimately, there's a multi-regime alpha, the whole alpha map, we believe, reflects this different alpha. Am I up to 35 minutes already? I don't think so.
No. So I just wanted to say that we're very close.
Yeah. So I have about 3 minutes left. So this slide is to say that there's endless interesting problems that I'm interested in, et cetera. Many other interesting dynamical effects. What's the role of repulsive attractive forces, thermodynamic scaling and dimensionality reduction, and dynamic heterogeneity, which is very interesting with, for example, observable consequences such as stretched exponential decay, decoupling, et cetera. And I'm not saying we've solved these problems. I'm saying these are other interesting problems the community needs to understand in a unified theory. And I want to conclude, though, from the general point of view, because I thought there would be students here, is that understanding these basic glass physics problems has tremendous implications for material science, and I believe also biology. And this is where a lot of my work is these days. If you go to a thin film, you have broken symmetry due to interfaces, and you have spatial gradients of everything. So for example, Mark Edgar has measured the diffusion near a surface of a thin film and found that the dynamics near the surface can be 4 to 11 orders of magnitude faster than in the bulk. And he has a clever way to figure out what the gradient is as you move away from the surface. And he's found and recently published that it's double exponential. So the diffusion constant depends on an exponential of an exponential as a function of distance from the interface. And it's this extra mobility at the surface that underlies his beautiful work in the area of ultra-stable glasses, where he can access low energy points on the landscape, effectively equivalent to super aging. My own interest is also many hybrid systems where you mix small and large particles. I'll just mention them. Polymer nanocomposites, where when you put in particles, you can tremendously change the polymer subsystem. This is relevant to tire technology, where the particles can reinforce the mechanics of the polymer. And then other problems relevant to separation membranes and batteries is how does something small, like a molecule or an ion, move in a polymer matrix or some other matrix? So it's a transport problem. And the real physics problem then is how is the motion of this object coupled or decoupled from the dynamics of the surroundings, which could be a supercooled liquid or a glassy matrix. And this is crucial for separation membrane applications and for advanced applications of ionic conductivity. And finally, in biophysics and cell biology, these are two of my favorite problems that I do think about. One is the cytoskeleton, which is the cell mechanics part of a cell, in which you have these rigid polymers, and they also undergo some type of glassy dynamics. There's, of course, all types of out of equilibrium physics also, but I believe glassy and also gel dynamics is crucial for understanding their mechanical properties, which are at the heart of their biological function. And then finally, if you make polymers out of rings, which is a topical subject, they undergo a collapse in a dense liquid, and they begin to look like a fluctuating soft colloid. And so it's been recently speculated based on computer simulation that you can have a glass transition in this type of system, not on the local scale, but on the macromolecular scale, and it's coined a topological glass. And so this is a fascinating challenge for glass physics, and also the question of whether it's related to soft colloid physics. And it gets even more interesting because this cartoon, which comes out of simulating ring polymer melt, where the different colors are different polymers in their own domains, looks just like what you see in a cell. This is chromosomes, where DNA has when it collapses, goes into territories and shows glassy dynamics. And so the impact of understanding this polymer physics problem could be very large on chromosome and genomic biology. So with that, I thank you for your attention, and I apologize if I ran a little long. Thank you.
Thank you very much, Ken. It was a very nice talk. And we have just a few minutes for questions from the audience, perhaps. We will have a larger round at the end, but if anyone wants to share a question, a comment, now it's the time. If not, I will ask to Greg and Pedro to contribute if they want as well. Magdaleno, do you have something to say or ask? No. Okay, later on. Greg?
Yeah, I was just sort of wondering from Ken's perspective, if you have a theory of the glass and everybody predicts the same thing, meaning the dynamics always seem to fall along a Vogel-Fulcher curve in equilibrium, what are the important predictions that, you know, how do you distinguish between the theories then? They all describe everything, which is why people, you know, arguing so much, because they can all describe the Vogel-Fulcher behavior, right?
Well, it's because they fit, right? I mean, I think the key, I think understanding the physics is deeply related to understanding the chemistry, really to be able to predict these things and to predict what happens when you change the infinite number of variables that we call chemistry. And by the way, we don't have vulgar Fulcher behavior at all. We have no divergences at finite temperature or below random close blacking.
Well, then you just gave me a prediction that's different than, let's say, if you like, RFOT or something, right? So you have a prediction.
I don't know of RFOT being able to predict that plot, for example. It could fit it maybe, but
well, yeah,
it's really questionable to me. I mean, if an RFOT, if what's in the Berthier paper that you have to now raise the configurational entropy to an exponent that might be system dependent, then I don't know. You know what you just said about VFT doesn't apply.
Okay, but you're still you've made a prediction here. So what happens outside the range? Because this is the normal experimental range, at least, that people try to predict one way or the other, right?
Well, that's what I tried to do here, Greg. I mean, I put it in here for you.
Yeah, that's what I wanted, right? Yeah.
So here's what we're limited by, is that we do not have the super accurate integral equation theory to get the structure at arbitrarily low points on the landscape. But because we've made all these predictions, Greg, which I know of no theory that makes these, you know, you can think of the physics 6 different ways. They're all interrelated. So if you can believe any one of them, right? So if you measure the mean square displacement going to low temperature, we make a prediction. If you measure the shear modules at low temperature, we make a prediction. If you measure about the structure at low temperature, we make a prediction. All of those things are predictions.
I think that's an important comment. There are predictions that you're making.
Well,
that other model that are quite different from other models when you get below TG, right?
Well, I mean, these apply in equilibrium, Greg.
But I realize that, but you can ask what happens in equilibrium below TG, whether or not you can actually measure it's another challenge, right?
That's why I said that we don't have a quantitative theory below TG, but certainly because we have these connections, if you just pick this one, since they're all equivalent in the range that they're applicable, then if the shear modulus sufficiently below TG, but equilibrated, approaches a constant, then we predict a crossover to Arrhenius behavior. So not only is there not a divergence, but there's a change from this supra-Arrhenius behavior. We don't have a quantitative theory for that because we don't have a quantitative theory of structure that low on the landscape.
Okay.
But just from the basic ideas of the theory, we have derived all of these. And I know of no other theory that's done something like that.
Okay, perhaps we can continue at the end with this discussion. We have a question from Adrian Huerta. Adrian, can you please formulate your question?
Yeah, thank you very much for a very interesting talk. I'm just wondering to know about the topological glass transition. I mean, I know a little bit about the Kosterlitz-Thouless transition from a crystal to something called an exotic phase, but I didn't hear about this glass.
Yeah, so so I know what you mean, but it has nothing to do with that. That has something, I think, also in 2 dimensions. Now, this word topological is used in polymer physics for the effect of dynamic uncrossability and conductivity. And it is a long history in polymer physics for entangled polymers of using this word topological. So the word here has nothing to do with topological insulators, or it has nothing to do with the topological things that your Kosterlitz, Thouless, et cetera, that you're thinking about. It's a word that comes out of polymer physics from people like Sam Edwards and Pierre de Gennes.
Okay, thank you very much.
Okay, then just to be on time, if you agree, we can move forward to our next, to the talk of our next guest, which I will and thank you very much, Ken. That was a very nice talk. And perhaps later on, I have a few questions, but perhaps at the final discussion. And if you allow me, then it is time to introduce our second guest for our roundtable. It is a turn to present the following contribution, which is experimental perspectives, testing the paradigms of the glass transition deep in the glass state, for which I would like to introduce gladly to Professor Dr. Gregory McKenna, which is a professor from the Department of Chemical and Biomolecular Engineering from North Carolina State University, and also a professor from the Department of Chemical Engineering from Texas Tech University. Greg, it is very nice to see you again, and I want to thank for your contribution as well. And
okay, so if everybody can hear me, you can see my screen.
yes.
Okay, so thanks, Christina, and it's good to see people from San Luis Potosi that I really had a great visit the last time when I was there, and I would like to hopefully be able to do that again in person rather than by Zoom. But right now, I guess we're going to do it by Zoom. But what I want to do is I want to talk to you about the ideas that we have related to the phenomenology of glassy materials out of equilibrium, because in reality, the glassy state is actually a non-equilibrium state. And what Ken talked about was really mostly equilibrium. And that's, I asked him that question specifically because what we think is if we understand this phenomenology of the non-equilibrium state, it can maybe lead to ways to test these ideas of what's happening in the very deep glassy state, where maybe, as you might say, nobody's gone before, where Ken is reluctant to say I'm making a prediction, but he is making a prediction because he's predicting that you're not getting a diverging time scale. He's predicting it happens at absolute zero, not at, let's say, the Vogel-Fulcher temperature. But to do that, we have to understand it. And so the question really becomes, if I look at these curves of typical relaxation time or alpha time as a function of temperature, or on an Arrhenius-like plot or an angel plot as a function of T over T infinity over T or TG over T, what's happening is that the material is showing very strong non-Arrhenius behavior. And this is what Ken was talking about, whether you have three domains here or not. What we know is when we get to this relaxation time of about 100 seconds, you fall out of equilibrium when you're doing an experiment, because your experiment usually is taking less than 100 seconds, or it could be 10,000 seconds as we show here. But what we see is then something like the relaxation times then fall over onto some other line with a very different behavior. The question arises, what happens as I go towards equilibrium? That would be one question. Another question you could ask is, what happens in this region if I do complicated temperature histories, or not too complicated, but just complicated enough that I can see interesting effects, okay? So where does equilibrium lie is also going to be the question. Can we find a way to answer that question, or at least address that question of whether or not it continues on this extrapolated line? Remember, Ken also told you the dynamics is extrapolated. People love this VFT extrapolation to the Couchman temperature or the Vogel-Fulcher temperature. But the question really is there a way to test whether or not that really happens? So here's how we look at it thermodynamically. Here's the idea of a phase diagram for a glass. We look at the specific volume or the enthalpy as a function of temperature. If we have a crystallizing material, we could have it freeze and we'll go through a first order phase transition. But sometimes we have materials that can't crystallize. So some polymers cannot crystallize. And so then we would just come down this line, or we can cool it rapidly enough that we get supercooling, like in orthoterphenyl. If I filter it a lot, I can let it sit at room temperature, which is below its melting point, for months on end, and it won't do anything. Okay, it won't crystallize, it will remain a nice liquid. So I can follow this supercooled liquid equilibrium or just supercooled liquid line down. And at some point it falls out of equilibrium because the dynamics are just such that it's too slow as I cool it to stay in equilibrium. So then I form a glass. My glass state is a non-equilibrium state. The glass transition is defined in case of the laboratory as the intersection of this equilibrium line and the line parallel to the glassy line from wherever I am. Now, if I let it age, and this is the non-equilibrium event, the material's out of equilibrium, it's going to want to get towards equilibrium. And so it'll come down this line. And at this point, this extrapolated line goes to a point that we call the fictive temperature. Okay, so that's one measure of the structure of the glass that we can take from the ideas of Toole back in the 1940s. The other way of thinking about it, and this is, I actually like this way, is the departure from equilibrium, delta, which is how Kovacs thought of it. And then actually it's the volume for him, or it could be the enthalpy, but it's like a volume strain. If you take it in volume space, the difference of the current volume from the volume in equilibrium, or the density in equilibrium. But the fictive temperature, also, these two are just simply related by geometry. And so you can talk about them in a related fashion. But so this is how we think about the thermodynamics. So in order to really understand the kinetics, we have to think about a series of experiments that were done back in the 1960s by Andrei Kovacs. It was actually, some of it was his PhD work in the 1950s in Paris, and he carried it out and completed much of the work when he was in Strasbourg, France. But he defined three signatures that are related to the kinetics. One is the so-called intrinsic isotherm, and this is a non-equilibrium experiment. So what you do is you start in equilibrium. So what you've done is you've come down to, call it TG, he called it T0. You let the material equilibrate. Now this is going to be in 100 seconds at this temperature. So it's going to, it doesn't take very long. And then you're going to jump down in temperature. And what you want to do is you want to watch this volume recover towards equilibrium. And you can watch it recover either by looking at the volume departure from equilibrium, which he called delta, as a function of time. And here it's a log time, and this T minus Ti has to do with how long it actually takes to change the temperature. And these are at different temperatures. For this was a polyvinyl acetate glass. And what you see is when you're at high temperature, so at 37.5 degrees, it's taking something like maybe a half hour or something to get into equilibrium. But as I go to lower temperatures, and that's at 25 degrees, this one, you can see that in over 100 hours, he's not even close to equilibrium. So you can see that these things are fanning out, and this is what you sort of expect as you get longer and longer times as the temperature comes down. Whether or not those times are as long as these times is also related to the question of whether or not we have this divergence. The other thing is that's important is that this data is from Simon and her co-workers on using enthalpy recovery, and she measured the fictive temperature, and the fictive temperature does much the same thing as what the volume departure from equilibrium does. And this was for polystyrene, so you can see the higher temperatures. So actually, it's worthwhile for people in the audience to realize one reason why the glass transition is so important in polymers, and there's just an incredible amount of work in polymers, is that we work very close to the glass transition when we use polymers. So like polycarbonate, which is considered an engineering thermoplastic, the TG is only around 140 degrees centigrade. So we're at 70% or so of the glass transition at room temperature. And these are materials we want to be able to use at high temperature if we can. So when they develop, and NASA develops a new material with a high glass transition, they don't work at room temperature. They work at, if the TG is 300, they try to work at 250 degrees. So they really do make an effort to increase the glass transition. And so we really do need to understand this non-equilibrium state, because that's where we're working. Okay, another aspect of the Kovacs signatures is the asymmetry of approach. In this experiment, what we do is we start out in equilibrium at some test temperature plus delta T, and we'll do a down jump to the test temperature to T0, or we'll go from T0 minus delta T, and we'll jump back up and do an up jump. So we have a down jump and an up jump. And if we had a linear process, the departure from equilibrium as a function of time should be a mirror image in the two. Okay, so here we see the down jump proceeds more rapidly to get into equilibrium than the up jump. So we have a strong asymmetry this way in the vertical axis. There's also a strong asymmetry in the horizontal approach to equilibrium. So what we see, the reason for this, and people understand this, at least phenomenologically, is the relaxation time depends upon the departure from equilibrium. And if I have a large departure from equilibrium that's positive, there's more free volume, people think. And so there's more room for the molecules to move around. And so you get a more rapid volume recovery. So that's what happens here. On the other hand, when you do the up jump, so you jumped up, you have a deficit of volume. So there's a deficit of space. And so the material is going to be more sluggish. And it's going to, of course, as it gets less and less deficit of volume, it's going to go faster and faster until it finally does still get into equilibrium. Now, the relaxation time in equilibrium is, of course, the same because it's equilibrium, right? Now, this is an incredibly important experiment from the perception of a framework for working with non-equilibrium systems and how they compare to equilibrium, because most of the work people do in glassy systems is over on this side of that phase diagram. So this is what I would call the classic aging regime on this side. But when I get up here, I'm in a regime where the departures from equilibrium are negative, or the fictive temperature, which I didn't write on here, but the fictive temperature in this regime is greater than the, the temperature of test is greater than the fictive temperature. And when that's the case, then you're going to be in a condition where the relaxation times are longer than the equilibrium times. So that's a very important idea that you should hang on to when we get into, when I talk later about the ultra aged glasses. The third experiment that was carried out by Kovacs in his signature, though, was the so-called memory effect. And in this, it's a two-step history instead of single steps in different conditions. So what he did was he first would bring the sample down to this temperature. You always start at T0 and jump down and let it age. So this would be the classic aging experiment. But for these other ones, what he would do is he would stop, age partially to equilibrium, and he spent a lot of time figuring out how that when he jumped back up, he got to where T equals TF, or the departure from equilibrium should be close to 0. And then he sat there. And if you had a single relaxation time process, you shouldn't get the memory effect, at least in the models that we use. And it should be monotonic if we missed. But look what happens. We get this crossover of equilibrium. This is the equilibrium volume, and yet the sample doesn't stay in equilibrium. It shows a memory, and it remembers which one of these, oops, sorry about the lines here, the numbers here, but it remembers how I got to that fictive temperature. Okay, so that's the memory effect. And this shows that, in fact, the kinetics lead to a glassy behavior, which is path dependent in addition to being temperature dependent. So it depends on not only departure from equilibrium and temperature, but it also depends on how I got there. And I don't have time, unfortunately, to go into the equations which were developed for that, but that's the so-called TNM model, or for Toole, Narayanaswamy, and Moynihan, or the Kovacs, Eklonis, Hutchison, and Ramos model. And I should point out the Carr model, the R from that is Ramos, and he was a postdoc with Kovacs in Strasbourg from Mexico. So a very important contribution. So later on, Strike showed that the relaxation times in the volume measurements compared to the way that the mechanical shift factors behave, you can also get a memory effect in the shift factors, which might be expected because as the volume is changing, you would expect that the relaxation times are changing. And Struck showed that within a reasonable experimental uncertainty, the actual value of those shift factors or the relaxation times, because the shift factors are a scaled relaxation time, are independent of the history. So it's actually with the dominant piece of that is that the free volume in his way of thinking determines the relaxation time. Okay, so I want to understand these Kovacs signatures, and will that let me address the Vogel-Fulcher common conundrum? Okay, in other words, can I really extrapolate the behavior to T Kautzmann or T VFT or T infinity, however you want to call it? Okay, so one way to do it would be to do experiments like the intrinsic isotherm, and that would be do it by brute force and age for as long a time as you're willing to wait and let the sample reach equilibrium. Of course, the advantage of that is it's direct. The disadvantage is it needs very long time experiments. And in fact, it's very hard to get much further below the glass transition than maybe 15 or so degrees before you run out of time. And I'll show you why that is the case. We call that the geological time or astronomical time problem in the experiments. And I think most students don't want to go more than about a few weeks for their experiment, well enough a few years. Or the other question, and this is understanding this problem of finessing this geological age problem. So if I know that when T is greater than the fictive temperature, we're in an upper bound condition for the relaxation times. And so that leads to the question, can we discover or can we manufacture extremely low fictive temperature glasses and make measurements of their dynamics to compare them with the Vogel-Fulcher extrapolation or with the theoretical prediction of behavior below the glass transition? So the brute force approach, long time physical aging. So this, as I said, it's an intrinsic isotherm type of measurement. These are data from long time ago from polycarbonate, where here's the VFT extrapolation to the equilibrium data. And here's aging data, and you can see it falls over. Actually, these data are close to equilibrium, and you can see they're not actually quite getting to the VFT extrapolation. So there's a question there. But at that time, we didn't recognize it. But here's the typical aging behavior. So at a half hour, even though I'm 35 or 40 degrees below TG, the response, the relaxation time is shorter than when I've aged it for 16 hours. Okay, and in this case, it's a whole order of magnitude different. And here we see the question that I'm asking is, if I age long enough, do I get to the VFT curve, or does it stop somewhere in between? And in 1999, so actually when I was still at the National Institute of Standards and Technology, Paul O'Connell and I did some experiments on this polycarbonate where we did the aging, and here we see at different temperatures, these are like the intrinsic isotherms of Kovacs, except it's in shift factor. And what we see is that as we go to lower temperature, things take longer, and of course, shift factors get bigger as we get to lower temperatures. So we're only about 10 or 15 degrees below the glass transition here. And this experiment took 23 days or something. And then we applied time temperature superposition to create master curves for all the scaled relaxation times versus temperature. And then we could ask, well, what happens to the scaled relaxation time, the shift factor, as a function of temperature or as a function of 1/T? And what we see is we get a pretty big deviation from the Vogel-Fulcher behavior. Okay, and that was something that, well, to us it says, Well, it seems to us that it's fairly clear that there's a problem with at least the BFT extrapolation. And it looks like at least over this 15 or 20 degree temperature range, we have either an activated process, which would be the 1 over T, or in fact, it's almost a straight line also in a log shift factor versus temperature. So that would mean it was an exponential in temperature rather than in reciprocal temperature, which might mean it's still different from the Arrhenius type of idea, but the activation energy. And shortly after we did that work, Cindy Simon and her student, Bill Sobieski and Don Plazek published some work looking at a compilation of data from the literature. And here is the shift factor versus 1000 over T minus T0, which is what's called a Fogel-Fulcher plot. And it should be a straight line to if it's really a Fogel-Fulcher behavior. And what they're finding is that the equilibrium data at about 15 degrees below TG has fallen off of this line. And that's similar to what I just showed you. So they're again seeing a deviation from the expected Fogel-Fulcher, and they're seeing it in a way that the times are shorter, not longer than the extrapolated Fogel-Fulcher behavior. So the geological time or astronomical time issue is in these prior experiments. One issue was that the depth below TG wasn't sufficient to be conclusive. So we're only 15 degrees below TG, and the Couchman temperature is maybe 50 or more degrees below TG. So we're not very far towards the Couchman temperature, if you're why they're the point of divergence. Well, so why not just wait longer? And so here's a reason. Even if I just assume an Arrhenius type extrapolation for time scales, they just get long very rapidly. It's really hard to do the experiment. So I'm going to take a material. I didn't just describe PVAC, but we've done work on PVAC in addition to other materials. And the sub-TG activation energy is about 220 kilojoules per mole. And this is typical of glassing materials anyway. They have high activation energies below the glass, at the glass transition. So what's the time scale? So in that particular set of experiments, it took us 22 days to do the first experiment to get it into equilibrium in 14 degrees below TG. If we go to 18 degrees below TG, well, it's a 77-day experiment. 28 degrees below TG, now it's almost 6 years. 38 degrees, it's 200 years. 43.6, I'm going to explain that in a minute why that we use that number, but that would be 1,628 years. And that's also a nice number because that's sort of the lifetime, people worry about whether or not cathedral windows flow, which they don't do, but anyway, look at how long the relaxation time is, just 43 degrees below the glass transition with a low activation energy. And 110 degrees, that's also related to what I'm going to talk about next. It would take, 9 times 10 to the 17th years to get into equilibrium, which is certainly beyond the lifetime of the current estimated lifetime of the universe. So how did we do it? Well, we're going to use an ultra-stable glass with a very low fictive temperature. And the glass we're going to use is amber. Okay, well, Mother Nature was good to us. We discovered an amber that would have a very low fictive temperature, it turns out. So I don't have time to go into the details of it, but it's an amber that's 20 million years old from the Dominican Republic. And it's a good kind to get because it comes in big stones. When they get older, they come in much smaller pieces. And here's what it looks like after we've machined it. So we can actually do viscoelastic measurements. So we can measure the relaxation time through ideas of time temperature superposition of the material in this upper bound region. And I'm going to show that again as we go, because it's going to have a low fictive temperature. And we're going to be able to work in between the glass transition temperature and the fictive temperature. So, okay, so here's how we did it. My student was Jing Zhao. Cindy Simon also helped work on this because we needed some thermal analysis done, and she's a true expert in that. And this is what people at the Smithsonian at some point thought that the world looked like in 20 million years ago. And here's this idea now. So here we have the glass, the resin. Of course, amber is a resin. It's an organic material that's a polymer, and it comes out of a tree in response to a wound. So it's a protective mechanism. It's not sap. And it first undergoes a cross-linking reaction, and maybe that cross-linking reaction goes on for a long time. But after 20 million years, it's done this aging at some temperature that's below its glass transition temperature. And of course, all we really need to know is where it's its fictive temperature. And in this case, here's the fictive temperature. And is the distance between the fictive temperature and the glass temperature big enough that I can actually interrogate the behavior over a reasonable window of temperature? Because below the fictive temperature, these are shorter than equilibrium time. So that doesn't test anything for me. I already know that when I'm up here, I already know they're shorter than Vogel-Fulcher. We already know that. The question is, when I'm over here and I'm in an upper bound condition, do I see something faster or something shorter than the Vogel-Fulcher, or do I see something even longer? And then, of course, as I get above TG, then I'm at the equilibrium time. So here's my 20 million year old amber again. And keep in mind, so what these are glasses, and they really do go slowly. And so what we have is the hydrostatic weighing difference is there's about a 2.1% difference in density between the sample as received and after thermal rejuvenation. And this just shows a DSC experiment. This very large excess enthalpy, what we call overshoot, is typical of a low fictive temperature glass. And we can calculate the fictive temperature. And it turns out that this fictive temperature for the 20 million year old amber was 42.6 degrees below the glass temperature. Slightly above, still about 20 degrees above the Kautzmann temperature or the Vogel-Fulcher temperature, but still a pretty big window, especially compared to the window that we had previously of like 15 degrees, right? Where we actually aged it into equilibrium up here. And here's the result. The green points are the data in the upper bound condition. So these are longer than equilibrium times. The one here near the fictive temperature arrow should be close to the equilibrium time, because at T equals TF, we have the equilibrium property. So that's where delta equals 0. And that's, remember, what Struck showed seems to govern the dynamics at that independent of history. But these are normal aging experiments, so they're lower bounds. And actually, it's interesting, as you cross the fictive temperature, this one there's sort of a little bump in the smoothness of the data. But the biggest thing is that you see that we get a very large deviation from the Vogel-Fulcher behavior. So this is 10 to the 6th maybe, and this is more than 10 to the 12th. Okay, so very, very big difference. So from our perspective, we thought that's pretty convincing. Molecular glasses, it seems that divergence of relaxation times may not be correct, and theories demanding such divergence need to be reconsidered, i.e. there is no ideal glass transition, or it occurs further than 43.6 degrees below the glass transition, at least in amber. Depends on the fragility, right? But so why not stop here? You know, what else could we do? Well, they say life is full of skeptics, and there were people who just didn't like what we found. You know, so glass transition is imminent, resistance is futile, you know, and the theory of the structural glass transition. In these papers, there was some critique of the amber data. Okay, they just didn't like it. So now there are exceptions to the skeptics, of course. There's a Maega model that does not diverge at above absolute 0. There's a Chandler model, so-called dynamic facilitation. There's Ken Schweitzer's model that we just had a very nice presentation of. The generalized entropy theory can be made to not diverge, okay, if they choose the right entropy model. But it turns out older ambers haven't proven to have lower fictive temperatures. We even looked at one amber that was over 200 million years old, and we're still doing work on amber, so we found some other ones. But right now, the oldest we've looked at is like 230 million years old. And that was in very small pieces anyway, so it'd be very hard to work with. But its fictive temperature wasn't as low as what the Dominican amber showed, okay? So we thought, oh, the ultra-stable glasses that Mark Ediger has made and that Ken showed a little bit of in the end of his talk, could they be optimized to have lower fictive temperatures relative to TG than the amber? So the present systems are not as stable as the Dominican amber tested here. So we got 43.6 degrees below TG, whereas Mark's record was 39 degrees or so below TG. The other thing is these small molecule glasses are extremely brittle, so they're difficult to handle for measuring the dynamics, at least using what I use, which is rheology or mechanical testing. So we figured out a way to vapor deposit an amorphous Teflon, and we met the challenge of when you do vapor deposition, you get micrograms of material. We met the challenge of using measuring the mechanical properties by using the Texas Tech bubble inflation method that we had invented some time ago for studying ultra thin films. So here's Teflon. That's the amorphous Teflon. So it's important it doesn't crystallize because we want it to be, be easy to handle with the glass without worrying about crystallization issues. And here, this just shows the stars are the reduction in the fictive temperature compared to the glass temperature. And you can see that it's much greater than what was observed in the other materials. And this was the amber at minus 43.6. But these were the data from the literature on vapor deposit small molecule glasses. So here we got, what we're going to look at is something that's got a fictive temperature of around 56 degrees below the glass transition temperature. So it's better than the amber. It also turns out that for the amorphous Teflon that we worked with, we estimated the Vogel-Fulcher temperature was just about 56 degrees below the glass temperature. So we're very close to the Kautzmann temperature. So again, back to my ultra stable glass and the unexplored region that we're interested in. And so, like I said, the challenge is to make measurements of this vapor deposited glass. We only get 0.1 to 5 micrograms. And here's what the bubble inflation material works with. I just show that these are nano bubbles. These are micro bubbles. Actually, these are 1.2 microns in diameter, and we can go to 10 or 20 microns in diameter, and we can go down to as small as 3 nanometers. But here we were using a couple of 100 nanometer thick because we wanted bulk-like properties. But when we apply a pressure to the bubble, we watch it creep, and the creep gives us information about the dynamics. And quickly, here's the result. We see here's the equilibrium data. Here's the Vogel-Fulcher fit to the equilibrium data. And here's the actual data of the in the window where we're in the upper bound condition. And so you can see we got way below the glass transition temperature. And this is very close to the Kautzmann temperature. So all the way down to the Kautzmann temperature, we find that we have deviations from the Vogel-Fulcher in this upper bound condition. And this also shows the amber data. This data, these lower points are below the lower bound condition, and these are the upper bound condition. So it's non-universal. So Ken, you can maybe give us some chemistry information. We also compared it to 2 models at that time. We compared it to the Maega model, and we compared it to the parabolic model from Chandler. And the Chandler model is sort of a cheat because it's a fit. I think, Ken, you would agree it's a cheat. It's a fit. We had an arbitrary parameter that TX in here that we, from there, make it an activated process, which is what they assume. So, but the Maega model, as we used it, didn't, even though it doesn't diverge, doesn't fit the data either. And this just shows a angel plot of the same data, and it compares it with some work that Mark Ediger did. He had 4 data points on physical vapor deposited in indomethacin, where he was looking at it devitrify, and he decided to fit this line through it, and that's what he thought was happening. This was his Arrhenius line, which fits just as well through the 4 data points he has, and he didn't actually go below TG. So what we see is the Fogel-Fulcher behavior is just not followed for either the amber or for the vapor deposited Teflon. And these are upper bounds. The equilibrium line, well, this point should be, it's right near the Couchman temperature. It's near the fictive temperature. It should be very close to equilibrium, but these points should be upper bounds to the behavior. So the ultimate question we need to ask is what's happening, because these should have lower times. So as we go here, are these going to continue to just sort of be on a straight line like this? Or is there going to be some curvature, which would imply that maybe something else is going on? We don't know. And we're working very hard to try and resolve that problem now, but we haven't done it yet. Okay, so now because we got this little bit of extra time, I think, I want to take a little bit of time to talk about considerations in colloidal systems, because Rosanna was going to talk about colloids, and I can't talk nearly as well about colloids as she can. But the question we want to ask is, are colloids good models in molecular glasses, and can we test that? So here we're going to address the kinetics of colloids after complex concentration histories to examine how they follow or not the Kovacs type signatures observed in molecular glasses. So of course it's hard, because in colloids, how do you do a rapid change in concentration? So that we figured out a way to do it with soft colloids. So, but the first question is, are they good models? And can we use our understanding of structural recovery in molecular glasses to look at the behavior of colloids? And the precedent of this for colloids as models for something like a structural glass comes out of ideas that you can see them. You can actually visualize with a confocal microscope the colloidal particles. You can see what they're doing. And so if it is a good model, it makes it very much something to think about. And this is the bubble wrapped ideas from Bragg and his co-workers. So this just to show you that conceptually the colloid is like the bubble wrapped to a glass, okay? So can we do experiments like the asymmetry approach or the memory experiment and the appropriate control variable? So in molecular glasses, the experiments are generally performed after temperature jumps, but in principle, they could be performed after pressure jumps or volume jumps. But of course, experimentally, those are much more difficult. In colloids, can we do concentration jumps? So one of the most important aspects of the dynamics of molecular glasses, the structural recovery, has not been previously examined in colloidal systems. And so can we use thermosensitive particles to create rapid concentration jumps in the vicinity of the glass transition concentration? And as I said, this is conceptually similar to the temperature jump histories Kovacs used in his classic studies of structural recovery in molecular glass formers. So what we would look at, we could do a jump in concentration or change in concentration and watch it age. We could do an asymmetry. It just shows how you would do it in concentration space, and then watch the dynamics. And so we're going to do this by using rheology. In this case, we've also done dynamic light scattering. In fact, these are dynamic light scattering. This is equilibrium behavior. These are equilibrium curves from dynamic diffusing wave spectroscopy. And we show for comparison, these were relaxation times from an earlier version of the Ken Schweitzer's model, where this is the hard sphere limit. And they do see deviations from that to higher concentrations, but also they see what's looking like it's going through a maximum actually. So here we don't get to that maximum. We just get to this plateau, which maybe is like one of these two curves here. And you see again in colloids, what we do see here is we get, in this case, about 4 decades. So that's an actual part of what Ken said, is this is not like the 16 decades or something we get with molecular glasses. So, okay, so this is rheology in a temperature jump for a thermo responsive colloidal particle. And so we do a jump, we change concentration, and we watch the creep response, the material as it ages, and we get time, aging time superposition. And here's the master curve. So the curves have the same shape. And so from that, we can get, this is for aging from 50 seconds to 12,800 seconds. And it had stopped aging by the time we were there. And so the shift factor is indeed a scaled relaxation time. And we can do that for the spreading of the curves. It's different, we see, in the down jump than what we saw in the intrinsic isotherm for the, this is similar to molecular glasses, but it's not as extreme. So this spreading isn't as extreme as what we see in molecular glasses. And what we see here is something we also see in molecular glasses, is that shear melting and physical aging itself have different kinetics of recovery. Okay, so that's an important thing. And we see that in molecular glasses and in the colloidal glasses, soft colloids. So, but we see here this spreading isn't nearly as great as in the molecular glass. It's similar. We have a strong decoupling between the alpha time, this is the alpha time, versus the time it takes to actually get into equilibrium, which is this time. And you do see some differences in molecular glasses, but they're not as big as what we're seeing in these colloidal glasses. But I think a more interesting point is that when we do the asymmetry experiment, so here's the equivalent of the down jump. So this is an up jump in concentration. And here's the equivalent to the up jump in temperature. We have a weak asymmetry in this direction and no asymmetry in this direction. Unlike, this is a polycarbonate glass where we have a very strong asymmetry in both directions. Okay, so that's something that needs to be investigated. And a question that needs to be asked is whether or not this is because in colloids, we're doing constant concentration, whereas when I do a temperature jump I'm doing constant temperature, but the volume is changing. So these are isobaric. So these are equivalent in a sense to isochoric experiments. And so in principle, what we've learned from the colloids is maybe we need to more closely look at the possibility of doing isochoric experiments in molecular glasses. We also get a memory effect. It doesn't seem quite as strong, but the data are much noisier than Kovacs's beautiful work. So okay, so I've tried to examine the divergence of finite temperature paradigm in glasses using a framework developed through the Kovacs signatures and the fictive temperature definition. The temperature dependence of the dynamics of a 20 million year old amber and of an ultra-stable Teflon film in the upper bound regime deviates from the Vogel-Fulcher WLF type of super-Arrhenius behavior, strongly supporting the hypothesis that dynamics do not diverge at T greater than 0 Kelvin, or at least not at, if they do diverge, it's at a temperature below the Vogel-Fulcher temperature. The present results are consistent with the idea that there is no ideal glass transition event. Thus, models which predict a finite temperature divergence in the dynamics or ideal glass transition should be reevaluated, modified, or being extreme, discarded. Data are actually good enough to differentiate among models. So I showed you the parabolic law versus Maega model. We've also looked at, we've looked at Ken's model, and we've looked at Jippy Deer's model, and we've looked at an old model from Ed DiMarzio and Arthur Yang, and those do do much better than these models do. Okay, so there's still some issues with them from the way that we handled them, but it's something that I think that people that do modeling should try and look at, because we can actually learn about what else we should do as experiments, right? And then the dynamics of colloids are somewhat different from those of molecular glasses, but similarities exist. We see the classic physical aging of the viscoelastic response in the intrinsic isoconcentration conditions. We see memory in the rheological measurements after two-step concentration jumps. And we see asymmetry of approach in the colloids, though, is close to symmetric, contrary to the large asymmetry observed in molecular glasses. And is this last difference between molecular and colloidal glasses related to the difference between isobaric Kovacs experiments and isochoric or isovolume fraction colloidal experiments? And this is something that has to be looked at in the future. And finally, future work, we want to investigate the fictive temperature responses for stable glasses produced by the PVD physical vapor deposition of different types of amorphous fluoropolymers. Can we get a TF below the Kaussman temperature? That would be something. So right now we've only been able to get it to the Kaussman temperature, but even that is exciting. Are other ambers available that are more stable than the 20 million year old Dominican amber? And I have a student who got stuck in China because of the pandemic, and she found some amber that looks like it is. So we're busy working on that. Can other measures of dynamics be used? So dielectric, flash DSC. Can other polymers be used? There is some work in the literature where people have looked at polystyrene and begun to ask questions about vapor deposited small polystyrene. There was some early work with high molecular weight material. It remained high molecular weight, but not as high as what they started with. And there's also been some more recent work on oligomers. We want to compare other models to the present results. So we're looking at like I said, the Schweitzer, Douglas and Fried, and so on. In colloidal system, why is asymmetry different than in molecular glasses? Can isochoric Kovacs experiments be performed in molecular glasses? You know, it's not easy to change temperature at constant volume and do it fairly rapidly. Okay, you need a big apparatus to keep the pressure high. Can Kovacs experiments be performed on hard sphere colloids? Because sometimes there's questions about what these mushy soft spheres are doing, like what is the volume fraction mean in those systems? And why are the alpha relaxation equilibrium time or equilibration time in colloids, why are they decoupled? And is there another thermodynamic parameter in colloids beyond concentration? And Rosanna didn't have a chance to talk about that, but she has been suggesting osmotic pressure is one possibility, okay? And there's actually some data in the literature from John Dutcher where they've done measurements of the osmotic pressure, but whether or not that fits with the simulations that Rosanna's been doing or not, I haven't had a chance to look at. And so with that, I can thank the people who have funded this and people who have spent time with me working on this problem. So with that, I can answer questions. So this was my students at Texas Tech before I left and moved to North Carolina, okay?
Oh, okay, thank you very much, Greg. Just a small comment. I thought you both were thanking Cristina Cáceres, who is right here next to me, and I'm just using her Zoom account. But just to be clear, I don't identify myself as Cristina or anything.
Oh, you're Luis. Yeah, you had to change your name. That's good. Yeah, Zoom can be very, very.
No, don't worry. It's just to be clear. I'm not making.
I was sort of wondering about that myself.
No, but now we have a brief time for a few questions, and I don't know if anyone else want to share some comment, opinion, or small question during these 5 minutes. We have a question from Ulises Torres Herrera. Please, Ulises, can you formulate your question?
Yeah, thank you very much for your very nice talk, Professor. My question is perhaps a bit naive, I think. I mean, for example, studying these ambers, which are 20 million years old, my question is, we think of that like a very simple story where the amber was created one day, 20 million years ago, and from then it has been kept at constant temperature and pressure. But for example, could we see now, today, a memory effect that was created, an event that was created perhaps 1 million years ago? I mean, can we see this effect altering, modifying our results now, our measurements now?
Okay, so yeah, so I mean, that's an interesting problem, because some of the ambers that we've looked at haven't even been stable chemically well enough physically. But the framework, at least, that we worry about is the fictive temperature framework. And so it's a question of how did we get there becomes less important, because the fictive temperature is the parameter that's determining where we are in this deep glassy state. But and I did look where the plate tectonics were taking the Dominican Republic over all these years, and the Dominican Republic was fairly, I guess, fairly stable. It just floated around, unlike some places where, like the ambers in Italy, you could ask that question because they're in a subduction zone where there's still active mountain building, and so they could be subjected to high pressure, right? Yeah.
Okay, thank you very much.
Ken, you have your hand up.
Yeah, I have my hand up. I think I know the answer, Greg, but is it, I don't think you, what do you have? I don't know how many systems you have now where you've tried to see when does the real data or some bound of the data fall off the VFT extrapolation. And is it true that for every system you or anyone else has ever tried to answer this question, the falling off happens almost right at TG?
It seems to be fairly close. I mean, there's some work done by Alexei Sokolov with who's his sidekick there,
Novikov.
Novikov, yeah. They actually did some work, and it's not in their work. It wasn't always right at TG, but it was always fairly close. Yeah.
Yeah, because I mean, there's nothing fundamental about TG. In some sense, it's a
yeah. I agree. Yeah, I agree. We were surprised that it happened sort of there. But it's
okay. But how many systems are there then? If you just don't count the Sokolov one, you've done 3 or 4, and other people, or like aging to equilibrium, even a little bit below.
So yeah. So okay. So no. Yeah. So we've done 4, I guess. We've done the amber. We've done the ultra dense Teflon, ultra stable Teflon, and we've done polyvinyl acetate, and we've done polycarbonate.
And they're all around.
Yeah, and we have some old data on epoxy that if you look at it, it looks like it's doing the same thing from this very old Lee and McKenna work that we weren't even looking at issues like that. We were doing aging, and we were doing aging close to TG, and so some of the samples were getting at least close to equilibrium, and they were certainly doing what that schematic thing I had up was polycarbonate, but it was doing something similar to that. So, and there's the polystyrene data that Cindy showed, Cindy Simon and Don Plazek. And there's also some data that we've looked at from Kovacs, and his structural recovery is pretty close to TG, and it's beginning to fall off of a Fogel-Fulcher behavior too.
And I don't know, is this a deep point or a crude accident, right? That's something about
I agree. I agree.
Happening right around TG for 5 different systems. That seems wild. I mean, it's intriguing. I have no idea why. But.
Yeah, and I don't have any idea why either. It happens. I mean, it could just be that's where sort of the limiting activation energy occurs, is when you're, everything's changing pretty quick there anyway, right?
Okay, thanks.
Thank you very much, Greg. If you agree, we can just move forward to the next contribution, and then at the end we can just discuss again with the whole audience. Or is there anything else that you want to comment, Ken?
No.
Okay. Then I think it is time. Thank you very much, Greg. That was a very nice presentation and contribution. And perhaps later I also have a few questions for you, but for the more, let's say, open discussion after Pedro. And now it's the time for our last of our speakers of the first round. It's the turn for Professor Pedro Ramirez Gonzalez from the Institute of Physics of the Autonomous University of San Luis Potosí. Pedro, would you like to share your screen, please?
Yeah, can you hear me?
Yes, I can. But I can't.
I need to prepare this thing.
But not your talk, right?
No. It's already prepared, just the screen. Sorry, let me try it again. Okay. Okay, do you see my screen?
Yes, thank you very much. So now it's the turn for the last round of this series of talks. And now, as I said, it's a turn for Professor Pedro Ramirez Gonzalez, whose contribution is entitled Towards a Fundamental Description of the Essential Features of Glass Transition. Pedro, thank you very much for your help and support for this organization of this meeting and also for your contributed talk.
Thank you very much. Actually, I can thank the organizers for inviting me because it's something like the picture, Well, but I can thank to Luis Fernando Elizondo, Magdaleno Medina, Edilio, Benny, Ricardo, and Cristina, who conforms the real organizing committee. So thank you very much, guys. In addition, I'm really grateful to Rosanna, Greg, and Ken for all the support and enthusiasm and interest invested in this issue. They took really seriously the invitation and helped me to organize a great session today. Unfortunately, Rosanna had a family problem that prevents her from joining us today. I want to wish the best for her and her relatives, hoping that everything will be resolved in the best way. Besides, I want to acknowledge the great work of Jonathan Lira Escobedo, because this talk is based on his work, always in collaboration with Patricia Mendoza Mendez and Magdalena, of course. The outline of my talk is the following. First, I want to describe some features that characterize much of the glass formers. Then I want to describe our approach to these problems. Next, I will show you some open problems, and finally a brief summary of the results and a take-home message, something like that. As you know, after the two previous talks, the glass transition phenomena have an overwhelming literature and many points of view converge on the problem. However, many of the glass formers present a set of characteristics independent of the specific nature of his microscopic components. Namely, a short and for sure incomplete list of such essential features are the following: the dependence of the final glassy state on the thermal history, the Kovacs signatures that fortunately Greg introduced, and the dynamic heterogeneities in the supercooled liquids near the glass transition temperature that actually can introduce it too. These issues forms a sort of checklist for any theoretical approach to glass transition problem, right? According with the standard knowledge of glass transition, in contrast with the equilibrium state, the overall properties of the glassy states depends on the preparation protocol. For instance, different cooling rates promotes glasses with different physical properties, as is shown in the picture in the screen, right? Another important thing is that by directly measuring of the evolution of volume, enthalpy, or fictive temperature, as Greg describes, through the variable delta, several important features of glass transition can be identified. These are referred as the Kovacs signatures, the intrinsic isotherms, the asymmetry of approach, and the memory effect or crossover experiment. The intrinsic isotherms demonstrate a non-exponential decay of structural recovery and the shift in the equilibration time during an isothermal relaxation, as the temperature of annealing approach to the nominal glass transition temperature. The asymmetry of approach shows the non-linearity of structural recovery, and the memory effect, the non-exponential behavior of structural recovery and the dependence of the kinetics on the thermal history. The relevance of this information, observation,
lies in the fact that several glass formers present them independently of its microscopic composition, although some difference have been observed for colloidal system, as Greg mentioned. Now, dynamical heterogeneity is another essential feature of the disordered materials, which emerged from experimental studies of viscous molecular liquids near to the glass transition. In these systems, local relaxation is measured by mechanical or dielectrical proofs, showing a wide range of non-exponential relaxation time. Indeed, using computer simulations to study supercooled liquids, we can observe that two important characteristics of particle motion inside the fluid are, first, they are highly intermittent, and the trajectories differ widely from one particle to another in the same system at the same time. So this is very important for many glass formers, even for glass formers formed by living cells or something like that. What we are making here in San Luis Potosí, well, we are trying to apply the non-equilibrium self-consistent generalized Langevin equation theory, a formalism that I will briefly describe later, to achieve an overall picture of these problems, right? Actually, the standard approach of statistical thermodynamics are not able to capture any of the features described previously. Necessarily, we need to develop extensions where fluctuations are included in the description of the system. One of the most important attempts for developing a fluctuation theory is the Onsager-Maslov theory of thermal fluctuations. However, such a theory is only useful for relaxation processes which are very close to equilibrium. In order to have a good picture of a strong deviation from equilibrium, observer need glass transition, we need to go beyond Onsager-Maslov theory. Making a great oversimplification, Onsager-Maslov theory uses a mathematical model of statistical processes called Ornstein-Uhlenbeck process, and the physical assumption that thermal fluctuations are described by such a stochastic process. What we have done is to extend the Ornstein-Uhlenbeck processes to non-Markovian situations and use a similar assumption that thermal fluctuations are governed by such extended process. I don't have enough time to go through the details, of course, but the interested people will see the paper that is referred in the screen. The previous formalism is general, right? And could be applied to any relaxation process. We applied, in particular, this formalism to the study of local density fluctuations in fluids. The result is the so-called non-equilibrium self-consistent generalized Langevin equation theory. I know that we need a shorter name, but it's what we have, which allows the description of the non-equilibrium fluids and their time-dependent properties. This theory contains two levels of description, one macroscopic for the local density average and the one-time correlation function, which is something like a time-dependent radial distribution function or structure factor if we go to the Fourier space. The other level is microscopic in the sense that describes the relaxation of the local fluctuations of the liquid through a waiting time-dependent intermediate scattering function. The two levels are connected by the time-dependent mobility, B of t, which is obtained from the microscopic level and governs the macroscopic one. The most important characteristic of the Nextlet theory is that it is able to predict two kinds of stationary states as a result of a relaxation process. Consider the main equation of the time-dependent structure factor at the top of the screen. If we ask for the stationary solutions, two possibilities arise. If the bracket becomes 0, then we are at equilibrium. In contrast, if the time-dependent mobility goes to 0, then we obtain a non-equilibrated, arrested stationary state, which can be identified with glassy states. The picture given by the theory is the following. Imagine the phase diagram of a system. Then points in this plot are like houses in equilibrium land, right? Now, if I want to go from point P to Q, I need to depart from the plot and explore a set of non-equilibrium states. Of course, if everything goes well, I can land to the another equilibrium state. But if a dynamic arrest condition is found during the relaxation processes, I will get stuck in a non-equilibrium state. This means that with the Nextlet theory, we are able to describe arrested fluctuations and non-equilibrium stationary states. In order to show the prediction of the Nextlet, we choose a simple model of a fluid, a soft sphere model described by a truncated Lennard-Jones potential, for which our calculation of local mobility at equilibrium coincides very well with computer simulations. And actually, we can determine the region for which the mobility becomes zero, which is the green line in the last picture in the screen. Below this line, the fluid is arrested and forms a solid-like state. Then we can study the relaxation process outside and inside the arrest region. As a first approximation to the dependence of the preparation protocol, we made a stepwise preparation protocol in which between each temperature change, we solve the Nextlet equations. The cooling rate in the model is defined by the total number of steps and the duration in each step. What we found is, in this case, is that when cooling processes is made above some critical temperature Tc, the system always finds the equilibrium state, no matter the cooling rate. In contrast, when the system is cooled down below Tc, a strong deviation from the supercooled liquid properties are found, and actually the system gets arrested in a stationary state, which depends on the cooling rate. In the first picture, you can see the relaxation of the maximum of the time-dependent structure factor for different cooling processes. The inset shows a sum of the final state, and we can see that there are a different final state for different processes. The dotted line in the expected equilibrium state, the dotted line, sorry, is the expected equilibrium state. And we can see that the system never find the equilibrium state. We can present this information in another way. If we define chi of t as the response function associated with the inverse of the time-dependent structure factor, we can obtain the two plots at the bottom of the screen. In both, the dotted line is the equilibrium value of chi of t. The left plot presents results for fast cooling rates, and we observe that deviations from equilibrium starts to appreciate above Tc. In contrast, at the right, we found that for slow cooling rates, the departure to equilibrium trends to Tc. In consequence, Tc separates the states which actually equilibrates for ones which are not able to equilibrate. Regarding to the Kovacs signatures, our first approach is the calculation of a model for a fictive temperature, which allows to compare with experimental observation in colloidal glass formers. Our model starts from the time-dependent structure factor equations, and with a lot of mathematics, we can write a relaxation equation for the fictive temperature, and a linearized version is at the bottom of the screen. Our model shares the same features at qualitative level as is presented in the picture, and in which we compare with colloidal with the colloidal version of Kovacs signatures that kindly Greg instructed me on that, and the comparison is quite good. It's very well. Of course, we need to improve our approach in order to get a more quantitative description in this case. Regarding the dynamic heterogeneity problem, we start for a linearized version of the diffusion equation, for which the time-dependent mobility is included explicitly. As you remember, we are able to calculate this time-dependent mobility from the Nextlet theory. Then we consider a system which is divided in many small cells, each one with a local time-dependent density. So we focus in two adjacent cells and how a prepared fluctuations, I mean, an initial condition with different density at each cell, relax to the final state after a cooling process. In the plots at the bottom of the screen, we present the density profile through the adjacent cells. Red lines describe the initial condition, where one cell has a different density than the other cell. And the blue line is the final stationary state after a cooling process. We observe that the theory predicts that depending on the cooling rate, the final state could become arrested, leading a arrested density fluctuation that could promote the dynamical heterogeneity inside the system. For the future, let me say that I'm so young and I really don't know. Indeed, I really appreciate the discussion and collaboration with all of you in order to define real target for future research on glass transition phenomena. And actually, thank you very much to Ken and Gregor for making some points about that. And the only thing I have in my mind is to improve the Nextlet theory to become it in a real theory for glass transition. So let me finish with the take-home message, and are that glasses can be described with an extended version of the unsaggered Maslow theory. It describes a number of conditions not described so far by any other first principles theory, like aging or the Kovac signatures, etc. And our first attempt shows that the Nextlet theory are able to describe qualitatively some of the main features of glass transition. So finally, let me thank all the LANINFES team for all the work and enthusiasm, to all the people that are working in the Nextlet theory, and a big thank you to all the participants for your attention. Thank you very much.
Okay, thank you very much, Pedro. Also, thank you very much, Pedro, for your presentation. Is there any question from, first of all, from the guests of the roundtable? Greg, Ken?
Can you hear me?
Yes.
Yes.
So I just have a very high-level question. I have a feeling I might know the answer, but I probably forgot. When you showed the evolution equation for S of K and T, it was local in time, right? There was no integration over history, right? Or did I miss that?
No, in this one?
Yeah.
No, it's local in
But
time.
this is a non-equilibrium structure factor.
Yeah, but it's waiting time dependent.
Yeah, it's waiting time. So it's not
dependent. Yeah, it's some kind of an overall relaxation of the whole structure.
Not S of K comma T, it's S of semicolon T, so it means something different, right?
Yeah.
So do you have is there a physical idea underlying, even for this, a physical idea underlying the fact that it is local in time?
Well, it's in reality an assumption. You know, we are making a local stationarity assumption, not equilibrium, stationarity. We think that the correlations, the two-time correlation function that is related with the intermediate scattering function are in some sense stationary at particular value of waiting time. This is much more like an assumption and a step way.
Yeah. Okay. All right. That answers my question. Thank you.
I guess I'm not being the theoretician here. I'm going to ask what's the salient feature that differentiates the two, your model and the Schweitzer model?
I think that maybe is that, you know, the Schweitzer models assumes that the deviations from the equilibrium line are related with activated processes. Yeah, the systems are actually in equilibrium, and some activation processes governs this kind of local dynamics. In this case, we are not assuming that, you know, the activation processes are not put inside previously. I think this is the most important difference.
And would you elaborate?
Well, I think there's multiple differences, but it'd probably take too long. Remember the work I did a decade ago really said that the dynamics was functionally coupled to an order parameter, which we took to be the dimensionless compressibility, which had its own evolution equation out of equilibrium. And because the dimensionless compressibility is trying to age toward equilibrium, that couples to the alpha time. And so then the alpha time becomes of this clock or effective time. So there is an integration over the past associated with that, just as many other phenomenological models are. So I don't know. I mean, it's not easy to verbalize the differences. I think there's quite a few of them, but I personally have not thought it through enough to say more.
Yeah, I'm agree. I agree with that.
It's
complicated. It's complicated.
Everything I do with activated processes. So yeah. that's also on the list, but there's more on the list than that.
Yeah, sure.
Well, then in that case, I gladly invite you to our third discussion table with Thomas Voigtman. And I think he will more or less clarify this point, given the fact that in essence, you can derive essentially the same equation with an MCT upon the same kind of assumption of local stationarity and so on. But I think we can come back to that discussion. It will be appropriate to discuss that in the roundtable number 3. And I just want to ask to the audience if there is another question or comment, perhaps. Let me see. We don't have yet any question in YouTube, right? No. Okay. So Magdalena, do you want to contribute, perhaps?
I like to contribute, but okay, I might actually intervene with respect to this transparency that Pedro showed and that Ken was asking. In principle, the equation satisfied by the static, the time-dependent destruction factor should also be non-local in time and so on. But within it was approximated by this, because otherwise the equations become too complicated and almost unsolvable. And so the idea was that within this non-equilibrium Onsager-Maglup's theory, the time evolution equation for the first moment and the second moment of the distribution are taken still without memory. But the fluctuations and the time-dependent correlations, those are non-Markovian. And for the equations that determine the mobility, which is this B of t in this equation on the right-hand side of the equation, which is the mobility, that involves, let's say, is like a mode coupling type calculation for the correlation functions, time-dependent correlation functions. And those equations do have memory. But the primary equations for this first and second moment, and this static destruction factor is sort of the second moment, is the covariance of the fluctuations, in this case of the density. Those are written neglecting, let's say, these memory effects. That has to do with Ken's question. The once we say that, I would also like to say we are now in the round table. I mean, in the minutes for discussion, aren't we, Luis?
Yes, I also wanted to say that let's say in regard this comment and so on and Kenneth's question. I mean, there are, as Magdalena just pointed out, memory effects, but they are actually, I mean, as part of the construction of the theory, taken into account. Not, I mean, not regarding this local time dependence, for saying in some way, but there are memory effects which are included, let's say, in the calculation of the B of t, which is basically related to the memory kernels of the intermediate scattering functions. Let's say another way to express the same idea is to say that actually the time dependence, the real time waiting time dependence of those memory kernels are dragged by the time dependence of the static structure factor. And that's more or less like a strong consequence of this local stationarity assumption. And I think it will be more clear because I more or less approximate what it is going to be in that round table with Thomas, Schregor, and Tommaso Rizzo. But I think it is a very fair and interesting question. And I think Schregor wants to raise a question, so please. Schregor?
Yes, just 1 second. Okay, so I have a comment on Ken's answer to Greg's question, and I have a question to Greg. So if I understood Greg correctly, he was encouraging Ken to use his theory to predict what happens below TG. And Ken was kind of hesitating, saying that we don't know whether integral equation theory is good below TG and so on and so forth. I mean, I have two comments. One is that in Ken's theory, TG, it has to be emphasized. He said it many times, but I think it has to be emphasized very strongly. TG is an arbitrary number that is defined by requiring that relaxation time is 100 seconds. There is no, physically nothing happens at TG. I mean, there is no transition, no nothing. So can use, in my opinion, he can use his theory both below and above TG, and he would predict equilibrium behavior both below and above TG. And as far as yes, but as far as the question whether integral equation theory or whether our understanding of local structure is good below TG, I mean, we don't know much even between, say, TC and TG, because most of our detailed understanding of local structure comes from computer simulations, and doing computer simulations below mode coupling theory is very difficult. Ludovic can now do them, but he can do them only for strongly polydispersed systems. So doing integral equation theory and various correlations for strongly polydispersed systems is another kind of worm. So I don't know. I mean, if in my opinion, if you say that you cannot trust static results below TG, how can you trust them below TC?
Okay, so I can answer that precisely. So we published a paper in Physical Review a year ago in which we use crystal avoiding simulation methods, advanced methods developed in Scott Milner's lab, that allows us to equilibrate, for example, the WCA or the hard sphere monodispersed fluid up to 58%. And then we've developed a improved closure, not PY, that actually reproduces those simulations very well to about 58%. So all I can say is up to 58%, we believe we have very accurate integral equation theory. I don't think this is well known. This paper is probably not that well known, but that's the situation. So then when you talk about TG, you have to go from, the mapping I do from hard spheres, packing fraction to temperature. But I think 58% is pretty high.
But that's TC. I mean, that's the dynamic transition.
What dynamic transition? We don't have any dynamic transition.
No, but that's if you extrapolated equilibrium data using power law fits, this is where you would put the dynamic transition. So what I'm saying
I view all
is,
that extrapolation as empiricism. So I mean, I don't
sure,
know.
of course.
So it doesn't. I mean, all I can tell you, Jagash, is if you take 58% hard spheres and you like map to orthoterphenyl, you're not at TG, but you probably at a relaxation time around 0.01 seconds or something, right?
Oh,
So,
okay.
so you really are in a situation with high barriers, at least with our theory, because barrier is a theoretical concept, right? I mean,
Yeah.
So, but I mean, this of course is the issue. Your point is correct that, at some point, everybody's integral equation theory is, well, anybody's integral equation theory is incurring errors. and we don't, and certainly at one point we tried to develop an integral equation theory that even had jamming in it. But of course it made all types of approximations. And so we're, as you know, as well as I do, we're at the mercy of what we get from dynamics. We're at the mercy of what we put in for the equilibrium.
Yes, absolutely agree. Absolutely agree. And then, okay, so now I have a question to Greg, and that relates to his absolutely amazing Amber experiment. And the question is prompted by what we do in computer simulations when we try to decide whether the system is or is not equilibrated. And typically, we do not look at just, for example, average energy, and we do not check whether average energy approaches its equilibrium value, but we also look at other quantities, because from experience we know that if you look just at average energy or density of the system, then they may approach equilibrium values, but the system is not really equilibrated, in the sense that, for example, if you look at time-dependent fluctuations, they may depend on where you measure them along your simulation trajectory. So my question is, how do you know that when where the volume, specific volume of your Amber approached its equilibrium value, how do you know that you are actually in equilibrium?
Oh, actually, we're not actually in equilibrium. I mean,
so you are not measuring. So you are then not measuring equilibrium relaxation times.
No. See that okay. So the assumption is that when T equals TF, even though the material is not in equilibrium, it's passing through equilibrium density or enthalpy, and the evidence we have from higher temperature measurements that I showed you from Struck is that the relaxation time in that condition is dependent only on the fact that it's at T equals TF, not okay. So it's dependent on that framework that we think the relaxation times depend on where we are, not how we got there. But so that would be the instantaneous relaxation time, but then it remembers where it was and it keeps going. And so then the relaxation time could change with time, right?
But Greg, isn't the point that you think you have bounds?
Well, the fact of having bounds, if I'm in a situation where I have a higher density than the equilibrium density, we think that leads to an upper bound, because all the other experiments we've done were in an upper bound condition, right?
Yeah, but isn't that like the essential thing? Because you don't find this big upturn of the time scale.
Right,
and
right.
You're arguing that the protocols you've used generated an upper bound. That's extremely powerful with regards to ruling out that upturn exists, as long as your protocol is okay. Right.
Yeah, no, I agree. Yeah, I agree. And but I was being asked specifically about the equilibrium issue. We're not in equilibrium except.
Okay, sorry, I misunderstood. Sorry, I apologize.
Yeah. I mean, what we don't know is where they go to, is if we could wait another 20 million years or something,
But they wouldn't
And
go
then-
above the upper bound, right? I mean,
They can't get, well, those are upper bounds in the sense that they're above the equilibrium
well, that's,
value.
yeah, so
Yeah,
you know the equilibrium is below that, and that's enough.
right.
If everything's
That's
solid
enough,
about
right?
that
Everything
statement,
has to be faster than what we have measured, right?
yeah,
Right.
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 Okay.
I mean, that's the important key, right?
Yeah.
Is there any other question from the rest of the audience besides Magdaleno?
No.
Already asked a question, but okay, if not, please, Magdaleno.
Yeah. Well, first of all, I'm really happy to participate in this conversation, and because I mean, we cannot go to meetings, and at least having at home is really great. Thank you very much for you guys for coming and for giving these lectures. I've enjoyed them a lot, and also particularly because our group is essentially theoretical. And we theorists, contrary to Ken is a chemical engineer, and he is.
No, he isn't. No, he
I
isn't.
have 3 degrees in physics, but I've never had a physicist mentor. My mentors were all physical chemists.
Okay,
And
yeah.
But I'm not a chemical engineer.
Sorry about that. But anyway, you interface every day with hard data, with real experiments, and your mind is always oriented to that, and much of your work has that beauty that you capture really complicated phenomena in rationalize with this with theories like the ones that you described. And Greg is eminently experimentalist, but we normally focus on the mathematical and physical assumptions and postulates and simple models and so on. And so we really need to be interfaced, if not as much as you do with actual data, as much as we can. And I say this because the work that Pedro described and those equations are the results of sort of complicated theoretical or mathematical assumptions. But in the end, there is a set of equations, just like in your theory or other theories. And then you solve them, and this is not a trivial thing. And for example, one area where we've solved those equations has to do with what we are talking about here, and that is highly dense liquids modeled by hard spheres, like the ones that you just mentioned, hard spheres at 58% volume fraction, and what happens there. And why? Because that's where the interesting things are happening. And that's where most of the fundamental questions await for an answer. But there are other regions as well. One of the nice things of our theory is that it is more of a kinetic theory rather than a theory for a structure. It's a theory for the kinetics, how a system relaxes to wherever it is waiting for it to relax. And then those equations, when you look at their structure, and Pedro mentioned that, for example, the time evolution equation for the static structure factor immediately tells you that there is the equilibrium solution, okay? But there are also other possible solutions which are mathematically different, but they turn out to be physically different. Now, you don't notice that so much in this regime of high packing hard spheres and so on, because, for example, the static structure factor, which is the equilibrium solution, looks completely like the arrested non-equilibrium solution. Both of them are stationary solutions at high packing fractions, but you cannot distinguish structurally, and that's probably one of the things that everybody claims when talking about the glass transition. The structure doesn't reflect the dramatic increase in dynamic properties, for example, but that only happens there. If you solve the same equations for a system like Lennard-Jones, and then you go away from this high packing region to lower temperatures, lower densities, then you have the gas-liquid transition, and then you have a completely different phenomenology. And let's say inside the spinodal region, these equations, let's say the equilibrium equations do not have a solution, I mean a uniform solution. But these equations tell you, but still there is a non-equilibrium solution, a stationary solution. And that reflects these spongy type structures that are formed by gels and so on. Now here it is the other way around. You do not even have the equilibrium structure factor to feed in, for example, in MCT. So you cannot say anything inside the spinodal region, but this theory, this non-equilibrium theory tells you. And those solutions are exactly what you see in experiments. And in that sense, but you can only see that if you leave, let's say, the stationary plane of equilibrium. You really have to go to solve the kinetic equations. Now, why I'm saying this? Because much of the questions and much of the discussion has to do with highly packed glasses. And I was going to ask you, Greg, because let's say these solutions near the spinodal is a spinodal decomposition that is arrested by the glass transition. And that is predicted by your non-equilibrium theory. And that corresponds to many materials, gels and porous glasses and so on. But then how much will this discussion today would change if we were to move from this highly packed, where only mostly repulsive interactions are the ones who dominate the dynamics, the caging effects and so on, when you start to see the effects of attractions. And I say that I pose the question because I'm wondering if there is also a large body of experimental work done, which I would like to know it, and it may be that there is much, or there may be not much work on that, on, let's say, the analog of gels and porous glasses, but at the atomic level. That would be my question for Greg. What would be the analog of that, and how much will the discussion today change when one moves to those materials?
I'm not sure I can answer that question at all.
Just some, I mean, that's fine.
I mean, in a way, it's Ken saying that hydrogen bonding liquids don't quite follow the same rules, right?
Yeah, I was going to ask Ken, but because he has applied his work to system with attractions.
Yeah, I mean, there's two things here, Magdalena. One, and you know this as well as I do, is you put strong short-range attractions on there, you can get apparent non-ergodicity transitions due to physical bonding, as opposed to the cage, right? You have attractive glasses, plastic glasses, dense gels, all those things. But, those things, those long-lived bonds only become long-lived when the attraction strength is high and the range is short, because that means the attractive force is big. And so every idea of van der Waals liquids breaks down. So I think if you're asking, are there gels in molecular liquids, or are there gels in polymer liquids, the type of thing that Greg studies and I study under dense conditions? I think the answer is no. I think the answer is what Greg said. The closest you can get is if you engineer a strong hydrogen bond interactions between the molecules, but they're just never strong enough or more rapidly varying enough or densely placed along the molecule to generate some gel-like behavior. But interestingly, people are still thinking about this. It's a chemistry problem. Is there a way to create molecules that could arrest, not because of caging or blocking, but they could arrest because of some engineered chemistry that just locks them in? I mean, silica is probably like that, right? Think of silica. It's a tetrahedral bonding object, right? It's not even dense. And so the reason silica becomes a glass is that the silicon and the oxygen interact, and there's an extremely strong interaction just because of where they are in the periodic table. Of course, generally you would call silica a glass, right? Not a gel. So how do you distinguish glasses and gels from other tough thing.
Yeah, probably when I say gel, I'm referring to this like bicontinuous kind of a structure in which.
Yeah, exactly. The same thing with your spinodal decomposition, right?
Exactly. Yeah.
I understand that your equations, they remind me of a little bit of Cahn-Hilliard equations for spinodal decomposition, but you have the dynamics in there through your B of T. So as you start phase separating, you have the possibility that the structure will arrest.
Yeah, that's right.
Arrest the phase separation, which is routinely seen experimentally in some systems, right? So
mostly in colloidal systems.
Very nice feature of your result, because your approach, because you're allowing the structure to evolve out of equilibrium, but then the structure out of equilibrium is coupled to the other parts of the dynamics also, right? And so that's
I mean,
why
the closest thing to that kind of thing might be the Vitramers that Ludwig Leibler has focused on recently, but those aren't real glasses, except when they go through their glass transition, because they're activated and they actually have the same activation energy as chemical bonds they're dealing with.
Bond to be stronger still comes apart on the experimental time scale. It still flows. But you know, when I teach about gels, I never tell people they're really solids. If you wait long enough, they flow. That's my view of reality.
Well, it depends on if it's a chemically cross-linked gel. You have to watch the language, because my rubber gel is never going to flow, right?
Chemically cross-linked is an amorphous solid, vulcanization and all that.
Right.
But all the physical gels,
oh yeah, for sure,
glasses, I don't believe there's an infinite viscosity at a finite temperature, right? I don't believe that. So I don't believe whether it's a gel or whether it's a glass. That's just my own belief, right? Which would touch on what you talked about, Greg, of whether there's a divergence at finite temperature. Because if there's a divergence at finite temperature, the viscosity would be infinite. And I think most of us would agree we call that a solid.
Actually, taking the occasion to make an announcement, in the fourth session on non-equilibrium rheology, this is what we have to say. Let's say, Leticia Flores, because the viscosity, as you say, in the gel region, or even in the glass region, it never really diverges within finite waiting times. And so it as you just said, it remains a very viscous liquid or very viscous system, and nevertheless, within finite waiting times, it continues to have a finite, not an infinite viscosity. Yeah.
I don't think you can measure an infinity, right? I mean, you eventually reach the point that the rheometer that can measure viscosity can't measure a viscosity beyond a certain value. And so it'll feel like a solid, right? I mean, that's my own personal view of those theories that have no divergences until you get to 0 Kelvin or random close packing. Yeah, the viscosity is unmeasurably high. So to a practical person, it's a solid, and we call it a glass. But as conceptually, I don't think it is. Right? I don't think the relaxation time is infinite.
That's the sort of argument you get when you just go look at Ferry's book, on polymer viscoelasticity. If you actually think time temperature superposition works, the only difference between window glass at room temperature and window glass at 1500 degrees centigrade is several lifetimes of the universe,
Exactly.
Yeah. But in some sense, I think the theoretical perspective of the theory that Pedro presented more or less agrees with Kenneth's perspective, in the sense that, let's say, of course, that there is no divergence of any quantity as relaxation time or viscosity or so on. And that is, let's say, because we only see those kind of divergences or divergence scenarios in the hypothetical case that we have infinite time to wait the systems to reach those idealized states or whatever. But in real life, we always have a finite time window for which these, let's say, theoretical descriptions predict something which is actually finite. So I would say more or less, it's a way to push your point, in my opinion.
No, that's part of the problem, but I think what you described is the issue of practical reality. I'm saying conceptually, if you could wait an infinite amount of time at any temperature above 0 Kelvin, I don't think there's a divergence. I mean, we'll never know. I think, right? Greg's trying to get to
unless we have infinite time, no. So
my feeling is there is no
finessing it.
It's not an issue. You don't see it because you can't wait long enough because it's a practical problem. It's because it doesn't exist. And this is what we argue about, right? Whether the Kautzmann, and then there's even people who will say, even if there is a Kautzmann transition, so what? The idea that there's a the configuration entropy goes to 0 doesn't have to mean the relaxation time's infinite. There's other ways to move. You don't have to exploit configurational entropy. And so this is like the deepest question, right? I mean, is even thinking about a 0 configurational entropy relevant? I mean, I'm arguing, I personally do not believe in the causal connection between thermodynamics and structure, but that's just my belief. We all have our own beliefs, and we all have to agree that there's no way to really know. Greg, I think, is trying to figure these things out, but it's
we're trying to find evidence. The thing is that I do think that if you look at that little diagram of the different, conventional glasses versus, deep glassy state kind of thing, or the unexplored regions, at some point, people are now making glasses, like Mark Edgar is, to try and use them in that unexplored region because they have unusual properties or potentially usable properties, such as better resistance to moisture absorption in a nanoelectronic system. So understanding it ultimately still is important. If you want to predict how long your SpaceX vehicle is going to work, and you're going to try and fly it 50 times and so on, you want to know how it's aging, and that's all the non-equilibrium behavior. And it's and even though and if you get the fundamentals wrong, I mean, even Ed DiMarzio would make the argument that you needed to understand he would say the thermodynamic transition of the glass, because he thought it was a thermodynamic transition. But the point was, he thought you needed to understand the equilibrium behavior theoretically in order to have a basis to understand the equilibrium, the non-equilibrium behavior. And we're using them in the non-equilibrium state. And we can actually have found ways to at least make small quantities of materials which have unusual depths in the energy landscape, right?
Actually, let me ask you this question, because when I talked to Mark Edgar and one of his data is on one of the slides I showed, he thinks he's incredibly close to the Kautzmann transition with these experiments.
In some of his data, he's actually below it.
Okay, but he's extremely close. But my question for you is, can you extract some facsimile of this configurational entropy for these systems that you're doing these analysis to get these upper bounds? So when you tell us 30 below or 40 below or 50 below TG, what does the configurational entropy plot look like? Have you done that already, Greg?
We didn't. We just calculated the entropy. We didn't calculate the configurational entropy.
Well, that's of course another difficulty.
Yeah, right. We just calculated the entropy, or estimated the entropy from the calorimetric measurements.
Yeah, it'd be really interesting to just do it.
Yeah, I mean,
we have a question.
But then it depends on which theory you use,
Yeah, I know. That's the other problem.
Guys, we have a question from Adrian Huerta. Adrian, please.
Thank you very much, Luis. I'm sorry, my English, I'm losing practice with my English, and I hope you guys can understand me. Regarding the Magdalena's questions, I have had an idea like 7 years ago. I proposed like an extension of the Ising model, where I have added translational degrees of freedom. So I have applied the rigidity theory, the theory which have proposed Phillips, Thorpe, and from the Arizona State University. So I have applied this idea. So what I did is count the numbers of degrees of freedom of the system. But this system is a magnetic-like. So in this model, I have obtained many different amorphous structures. I can show. I have not prepared nothing, but I have the paper and I can send it to Magdaleno. Probably is related with this idea. So my point is probably a magnetic system can produce some structures like that. So it's only a point to make, which I want to point it out. And thank you, Luis.
Yeah. Well, my understanding is people are still arguing about spin glass physics, which is where essentially a lot of the entropy crisis theory per RFOT came from. So I don't know whether the magnetic system will allow you to do something you can't do with structural glasses. And then there's the question of, is it universal anyway? I don't know, right? I mean,
well, and the spin glass stuff, they evolve forever, right? They're more like some of the stuff that you do, Magdalena, when you get below a certain temperature, right? Then things age forever, right?
Well,
they never stop.
Forever
right?
when the experimentalists stop looking, you mean? Yeah.
Well, you know, but I mean, longer than what they expected they had to anyway. Right?
Yeah, yeah.
Yeah.
You may know, I'm not familiar with that specifically.
So it's yeah, I mean, it's actually, yeah, Ken, I think it was you that said something that at the glass transition, nothing happens, right? At TG plus 1 second or TG minus 1 second, you know, or one degree or 1/10 of a degree or whatever, you know, it's not like you're going from ice to water, right?
In fact, your colloid experiments sort of with your 4 orders of magnitude, that would be analogous to doing an aging experiment far from TG, far above TG in a thermalized system.
Almost, yeah.
And so there's nothing really fundamental about it. All your signatures were weaker and this, that, and the other, which I think is what I would guess. But I mean, just the fact that you see those signatures, you know, I mean, that's intuitive to me.
Yeah, well, I mean, it's like, you know, I mean, remember Fogel, he was working with like oils and stuff. He didn't do things that he ever thought was going to become a glass. He just was at the range where things started to not be simply arenas, right?
I didn't even know that.
Yeah. Fulcher was the one who applied it to the glassy systems because he was working at Corning. And he cited Fogel, and at that time, Taman was very well known at that time. And he told them, I'm working on the same kind of equation. And so they decided they were nice and they put his name on it because he hadn't even published yet, right? And so, I mean, and it should only be the Fogel equation because Fulcher acknowledged Fogel in his paper and he, you know, cited him. And it was like 3 years later or something. So, you know, which at that time was, of course, very rapid, right?
On your homework, Greg, I never read those original papers.
Well, and then they got Hess in there too, because Taman and Hess were on one of those papers, right? So they got the VFTH expressions, right? And I got into when I wrote that review article for the Rubber Chemistry and Technology. You know, I went back and had Google Translate working on the German stuff, you know, and so yeah, it's pretty interesting because the people back in the 30s, Nernst was worried about it, right? You know, because they recognized there was some issue with the entropy, right?
Yeah.
And they did already then they did. And so, and I think Nernst was worried because he thought it might upset the third law.
Oh, well, yeah. Especially if it was crystallizable material, right?
Right. You know, and then the people in polymers in the 40s, so they were doing rubber, right? So rubber turns into a glass at low temperature, and they were seeing all this behavior that, you know, ultimately people later called second order transitions, right? But they were smart enough to not call it that. and then they were looking at the thing in the sort of the same way that Nernst was, right? So, and this is back in the 30s, right? Even if you look, so some of it's very interesting, the amount of thought and work that's gone into these problems, and maybe they haven't been resolved, except in the sense that I was at a meeting once where Frank Stillinger just said that the glass transition doesn't exist or something like that, you know. So
well, anyway, maybe we're diverging here.
yeah, right. That's the divergence. Right.
Random walking. I'm not sure what it is.
Well, I don't know.
The other day in a
almost
meeting,
7
I was asking some of our colleagues, let's say, when will we know that we have understood the problem? Which are the fundamental questions that once they are answered, we can say, okay, we're happy, we understand.
If you're lucky and you go to heaven, then they'll tell you, right?
It's an asymptotic question.
I mean, but that's terrible. That's all the time. That's the answer I get. I mean, one answer was, but if that happens, then we will not have a job anymore. and I say this because I think that is important to. And I remember this paper by Greg, the review paper by you, Greg, and a number of people who really made a catalog of pending issues related with the glass transition. And it would be good to single that down to a few questions, let's say what are considered the most fundamental ones. If I ask you, Ken, and Greg, which would be the most fundamental one? The one that you would say, this one at least should be answered, and that is?
First, figure out whether it's thermodynamics or not.
Okay.
I mean, can there be a bigger difference than saying a dynamical transition? It's like critical phenomena, right? We all agree in critical phenomena that the divergences in dynamic critical phenomena are driven by approaching a thermodynamic critical point with a diverging length scale. And people try to make theories of the glass out of that. But, you know, we have no agreement on this, right? Of whether we can understand exponentially growing timescales from thermodynamics, or thermodynamics, it's correlated because everything's correlated with everything, it seems, in the glass problem. It's correlated, but I don't think, but is it the fundamental way to think about the problem? And you know, so to me, that would be a good place to start, because then you could be partitioning approaches into things based on dynamical slowing down without thermodynamic critical points or phase transitions or zero entropy versus ones that do. That would be
what is the fundamental nature of the glass transition? Either thermodynamic or dynamic or kinetic.
Yeah, there's certainly thermodynamic consequences, but we're talking about the fundamental driving force as you go down the landscape of a liquid.
Yeah, well,
right?
I mean, I agree with you. I think that's probably the thing. But keep in mind, you know, we look at it as coming out of the liquid state and going down, avoiding crystallization and going into the, you know, whatever, the non-equilibrium glass, and then so on. You know, I remember the first time I was at a meeting where there were a lot of metal glass people. And they look at it at when do you get a crystal so disrupted by putting in defects that it becomes a glass? You know, at least that's how they were looking at it then. I don't know what they're doing now, you know, because they have miracle rules and stuff like that.
Amorphous solid transition.
Yeah, see, so there's a completely different way of looking at the problem, because they're so, and of course, in a way, metals people can look at it more like colloids, because now they can actually visualize the atoms, right? And
putting crystals in is just a bad idea, because there's plenty of things that don't crystallize on any time scale you care about. And I don't think that's part of the physics.
Well, I don't disagree, but I'm just saying, though, that there's a whole different way of looking at it in that community, and they do things fairly differently, even though phenomenologically, when they do the experiments we do, like enthalpy recovery and volume recovery and so on, they get the same results, right?
Yeah.
So the kinetics all look the same.
Crystallization of spheres is so easy. I mean, it's even hard to crystallize orthoterphenyl, right?
Right. That's right. You know, so we have,
these are like chemistry questions almost, right? I mean,
yeah.
I mean, so,
Okay, guys, I think I will have to ask you for stop, not the discussion, but at least I need to stop the recording for our broadcast in YouTube, but we can just continue here, or we can continue in our next roundtable. So before doing so, I would just want to thank you very much again for your contributions, and we can continue here, or we can continue in our next roundtable.
I have dinner in about 15 minutes.
Yeah, I've got to go too, because it's 7 o'clock out here. So yeah.
Okay, then let us stop here. And again, I want to, on behalf of the organizing committee, I just want to thank all of you for your very nice contributions and your willingness and openness for this discussion. And I hope to see both of you in the next roundtables soon enough.
Okay, well, muchas gracias to you.
Yes, yeah, muchas gracias. I can say that. Yeah.
Muchas gracias a ustedes. Thank you, Ken. Thank you.
Thank you, Ken. Thank you, Greg.
The rest of the audience.
Okay, bye-bye.
It was a pleasure seeing you.
Yeah.
Adios.
Yeah, good to